And I've got a few announcements to make first. Okay. Got some sorting to do, but I'm pretty sure you didn't get a copy of the lab, right? Okay. And anyone else did not get a copy of the lab. Okay. Now, I'll depend on y'all to remind me how far we got in the lab. But before we do that, this will allow people a few more instances to come in. So I think I'll go on and start this with current slide, and we'll come back to this in a minute. Second.
We finished the core concepts on this.
On the what?
On this PowerPoint.
Yeah, we took care of the PowerPoint that we got done on the lab.
Yeah.
Was there a slide before this then?
Huh?
Was there a slide before this?
Yeah.
Okay, we got it.
Huh?
We got that.
Yeah, we got this. I think we were on this slide.
Yeah, that's what we were on.
Yeah, okay. We're not there yet. We're going to finish the lab first. But before we even get going on the lab, here's it's about time type of announcement. Okay? I finally got I think I already had your syllabus out on Blackboard, didn't I? Okay, it was out there. It's under syllabus, which when you go to Blackboard for this course, there's a series of tabs over here. And depending on how big your screen is, how far down it goes. But near the beginning, I think it's like the third tab, or at least on the instructor side, says something about syllabus. That's where I put your syllabus. And I believe it's the next tab under there, or shortly thereafter. There's another one that says instructor information and schedule or something like that. That's where I put my locator card, which shows when I'm on campus, off campus, in class, out of class, lunch, which campus I'm on, that kind of stuff, all 5 days a week. It's a tab either right under the syllabus tab or shortly thereafter. And then finally you get down, about maybe 2/3, 3/4 of the way down the page, depending on how big the screen is. And there is a tab there that says class handouts and more. So what's there is the research paper instructions, okay? These 10 pictures from the Hubble Space Telescope. They're just there for fun. They're just beautiful pictures. Then the space objects in perspective. Really neat little file there that shows, various things. If you go through it, it's incredible. Okay. And it's relative sizes. And then I think the next are all the PowerPoints that we'll be doing all term. Chapters 14, 15, 16, 17, 18, 19, 20, 23, and 24. Okay? And then finally, the link to the YouTube videos. So if you haven't been here, you can go back and see and hear everything we've done in class. You can't see me wave my arms, but you can see everything else. You've been in my class before. You remember how the YouTube videos work. Okay, so those are all set up. So the class is pretty much set up for the term. Okay? May have other things we'll put on later, but that's it for now. Okay. Done. Okay. You're the first class I've got completely out there. I've got some of the others mostly done, but yours is the first I completed totally. Okay, now I go on the count on y'all to remind me where we left off. I know and by the way, you might want and I put as much of the lab as I could on YouTube videos, so you'll have to go back and listen to the last class lab. I believe it says, I think it just says Lab 1. I went to either pause or start the video, and I hit the done button rather than I hit the wrong button. It closed it out. I had to bring it back up. I believe all the lab is on one video, and it's just called Lab 1. So you should be able to find that. Okay, and on that, we talked about some of the words on page 359. We did the first problem on page 360. The second, third problems on page 361. We talked about the 362 stuff. We did the 3 questions on 363. And we passed around the star guide, and y'all found for me 6 stars, or at least something close to 6 stars, 6 constellations, or something close to that. And then we did, that's on page 364. On page 365, we did question 10. I think we did 11, and we did 12, right?
We did all the questions on page 365.
Okay, that was 10, 11, and 12, right?
Yes, sir.
Okay. Okay, and we did the table on 366, the 3 tables. Those are all filled out. And I think we did 13, didn't we?
Yes, sir. We stopped at 14.
Okay, we did not get to 14. That's what our memory was, but I couldn't remember for sure. Okay, now, I was afraid of this, so I'm going to have to pause this for a moment and minimize that and go to this. It's going to take a while because it's a PowerPoint. Look at that. Didn't take long at all. Okay, and we'll go from current slide. All right. What number 14, bottom of page 366, is calling for. Now, we don't have a celestial globe, but what we're going to do is I'm going to draw a picture. What range of declinations can stars have so that they never set, that is, are always above the horizon? And we're doing it from our latitude. Okay? Now, let me get my pen set up. Okay. Here's going to be our little globe here. That's not a very pretty globe, is it? And here we stand in Bessemer, Alabama. Okay. And we are at, does anyone remember our latitude? 33 degrees. I believe it's 43 minutes. And no. Here's a Alabama Atlas and Gazette, whatever a gazetteer is. And Bessemer, Alabama is at latitude thereabout anyway. 33 degrees, 23 minutes, 45 seconds. 33 degrees, 23 minutes, 45 seconds. Okay, let me get that corrected. Okay. 23 minutes, 45 seconds. Okay. There we are, standing here in Bessemer, Alabama. Okay. Now let's draw our horizon here and draw our celestial sphere, or at least the hemisphere. Okay. Not a very pretty one. Here is our zenith directly overhead. And the celestial equator will be just like the equator is here. This is the actual equator here. And the celestial equator will be something like this. And that will also be 33 degrees, 23 minutes, and 45 seconds from our zenith. Right? Now, we're asking for what range of declinations, and where is declination measured from? Does anyone recall? Celestial equator, from the celestial equator. So what range of declinations can stars have so that they never set, that is, they're always above the horizon? Okay? Now, before you answer that question, I'm going to ask another one. What star never sets, is always above our horizon? The North Star, you're absolutely right. And it's over here, okay? There it is. It's Polaris, or North Star, okay? And that's a really ugly picture, isn't it? Does anyone remember its altitude above the northern horizon? This is the northern horizon. This is the southern horizon. First question we did on this lab today, the other day. This is actually our latitude. 90 well, it's
90 degrees from the celestial equator.
right. Okay. Say that one more time.
90 degrees from the celestial equator.
Yeah, okay. The North Star is always 90 degrees from the celestial equator. We'll be using that fact in a minute. But its altitude is exactly our latitude. Okay? Look at that first question. We said that if this is alpha here, this is alpha here. Remember? So that and that are the same. So this is 33 degrees, 23 minutes, and 45 seconds. Okay? Now, if the North Star never sets, because it stays right there, doesn't move much anyway. Get your name, please.
David Russell.
One more time.
David Russell.
Wilson?
Russell.
Russell.
Yes, sir.
Okay. Last name Russell.
Is it?
Okay, were you in the class with earlier? Or have you just added?
I just got here.
Okay, that's what I was going to say, because I didn't have you on the roll before. So, Russell is the last name,
Yes, sir.
and David is the first name?
Yes, sir.
Okay. Okay, I can't read my writing here. My pen's skipping on me. So this is your first time here. Okay. This is interesting because Ladarius Armand Thomas was here the first day, but he's not on the roll anymore, so he must have not be here anymore. So let me take a time out here and fill you in on where we are, and where we're going, and what we'll be doing. And meanwhile, give you a lab. Okay. Now, sorry, the rest of you, a little bit of time out here so I can bring David up to speed. Okay. First, and it's Physical Science 111 here, right? Okay. It's a mini-term course, right? That means we basically, believe it or not, today is the beginning of our third week of material, okay? Because every class day is like a whole week in the normal term. So this is in our third week of material. But don't sweat that, we didn't get that much done in the first two. So here's where we are. First, you know about Blackboard? How to use it and everything here. You go to Blackboard in this course, and I've just gotten it out there, so it's just there. When you go to Blackboard in this course, there's a series of blue tabs, or at least on the instructor side, they're blue. And like the second or third one here says something about the syllabus. That's where I put the syllabus. So you can go there, you can read it, you can follow it, you can do anything you want to with the syllabus. Okay? The tab either right below it or very shortly below it says something about instructors, schedule, and something another. Well, that's where I put my locator card, which is when I'm on campus, off campus, in class, out of class, lunch, which campus I'm on, that kind of stuff. That's in that one. Those are the only two files in those two tabs. Then you come down quite a ways here, and there's one tab that says class handouts and more, or something like that. Okay? And if you go to that tab and click on it, you'll see a whole bunch of stuff. First thing there is a research paper instruction. This class has a research paper, and it's a mini-term class, so you've only got, now 7.5 weeks to do it, okay, because it's an 8-week term. So please get it done, get working on that. In fact, if you'll give me a your paper topic, anything you want to that will be covered in this class. That would be astronomy, geology, earth science, meteorology, climate science, oceanography, lots, huge range of things. Anything up there that interests you, pick a topic and do it. Okay? So, the instructions are there under class handouts and more. After that, there's 10 incredible pictures taken by the Hubble Space Telescope several years ago, just for fun of looking at. They're just that pretty. Okay? Then there's another one that's pretty informative. It's a file called Space Objects in Perspective, and it just gives you an idea of the relative sizes of a bunch of things, like the Earth and the other planets and the Moon and the Sun and the other stars and galaxies and stuff. It's just incredible. It's just a real neat file. Nothing to be tested on, just fun stuff. Okay, and then after that are all the PowerPoint shows that we're going to have all term. Chapter 14 we've already done. Chapter 15 we're in now. And then chapter 16, 17, 18, 19, 20, 23, and 24. Okay? Those are all coming up. And then the final file that I can recall is the one that says Physical Science 111 YouTube videos. Okay. That's the one you probably want to go to fairly soon, because in that, every class we've had so far, see, right now I am recording. Okay? Records everything I say and everything that's projected on the board. And we went through the syllabus. We went through the research paper instructions. We went through safety. We went through all sorts of stuff. And we also went through chapter 14, all the lectures, all the PowerPoints, hearing me talk about them, writing on them, and stuff like this. The earlier ones that are just there as files, they're just static. They're there. These you hear me talk and explain things, and we talked about things. And then we started the lab last time on chapter 14. That's what you got a copy of there. Now, unfortunately, last time I messed up like twice at least. And when I went to pause the recording, I hit the button. No, I had already paused it. And when I was supposed to go and hit the button to take it off pause, and I hit the button that closed it out. So I ended it too soon, opened it back, and then closed it again and it opened it back. So the talking about the chapters on the earlier ones, the ones that says chapter 14, anything, and the ones on the lab just says lab 1. Okay? And if you go to that one, you can listen to it and probably answer everything if you turn to your lab. We talked about page 359, okay, right in front of you, okay. We talked about 360 and answered the question 1 at the bottom of 360. We talked about 361 and answered questions 2 and 3 on 361. We talked a little bit about 362 and 363, answered the questions on page 363, 3 questions bottom of the page. And then the various people in the class located stars on my star finder and gave the star names or the closest thing they could get to them, because a couple of them weren't on there. And then constellations, I think all but maybe 1 or 2 of those were on there, but we gave one close to it. And then we went to page 365 and answered the 3 questions there, 10, 11, and 12. Filled out the table on page 366, the 3 tables, and we answered question 13 on 366. And we were just in the process of doing question 14. Okay? Now, that's where we are. That's where we're heading. As soon as we finish the lab today, we'll get back to chapter 15 that we started last time. The last 30 minutes of today's class is the test on chapter 14. So the 2 of you who haven't been here and haven't had an opportunity to hear any of this, if you don't want to take the test today, you don't have to, but you have to come see me sometime during office hours, and you'll get those on. I've got my locator card on my door in my office. That's in 265. If you know where the orientation classroom is, just across the hall from that. Or you can look on Blackboard and get my locator card. And so it's come time. Now, most convenient times, I would think, is right before class, 11:15 to 1:15. I have office hours on Tuesday and Thursday. And then right after class, 5:45 to 6 o'clock. But I can stay later than 6 if you need me to. Okay? Now, I also have office hours on Monday and Wednesday. Monday, 2 to 6, and Wednesday, 2 to 4. And I'm on the Birmingham West Campus on Fridays, 8 to 12. So whatever time fits best, come and see me and get your test made up as soon as you are able to view the material and go for it. Okay. And by the way, for everybody, a reminder, but for you too, you can bring with you to every test that we have a formula and equation sheet. Anything you want to write down on a piece of paper, you can bring for the test. I did tell y'all that, right? Okay? And for the test we're having today, you can bring your formula and equation sheet. And if you haven't worked one up, I guess you could be doing some of that while, I say this, while I'm talking about chapter 15. It's up to you, okay? Okay. But anyway. All right. So what we're doing, and we did this in other parts of the lab too, and we'll be doing it in the next lab and for a while now. We're doing our celestial horizon. This is supposed to be the globe down here, and this is the equator here, and we're here at 33 degrees, 23 minutes, and 45 seconds. That's our latitude, how far north we are of the equator. And on the celestial sphere, that's how far north our zenith is of the celestial equator, 33 degrees, 23 minutes, and 45 seconds. And at right angle with the equator is the North Star, the North Pole. So therefore, at right angles with the celestial equator, you'll find the North Star, Polaris, North Star, whatever you want to call it. There it is. And it's fixed in the sky day and night, but you can't see it in the daytime, but at night, it's right there. And it stays there. Now, all the other stars move around it. Okay? They really don't move around it. The Earth spins, and it makes it look like the stars are moving around it. But they go around it. And the question here is, on number 14, bottom of page 366, we don't have a celestial globe, so we're using this picture here. What range of declinations can stars have so that they never set, that is, are always above the horizon? And we already named one that never sets, and that is North Star. And what's its declination? What's its angle above the celestial equator? 90 degrees. You're absolutely right. Now, the question is, what range of declinations are these other stars? And just to give you an idea, they're all the stars in here. They never set. They just move around that. So they would go up here too. So whatever they are below here, they're above there. So what we have to do is subtract this. Okay? How's going to be the best way to do that? Perhaps, let's see. Yeah, just subtract this from 90 degrees. Because the declination of the North Star is 90 degrees. So let's subtract this from 90 degrees, and that would be, put you over here, and then all the stars between here and 90, they would rotate around the North Star and never set. These out here are up half the night and down half the night. These here just go around the North Star. So let's do that. Let's take 90 degrees, but when you're subtracting, it's usually easier to subtract from 89 degrees, 59 minutes, and 60 seconds. It just makes the subtraction easier. Because what's 60 seconds? 1 minute. And if you add 1 minute there, you get an hour degree.
Oh, yeah.
And you add that to that, and you get 90. So that's another way of expressing 90 degrees. And we subtract from that 33 degrees, 23 minutes and 45 seconds. And what's that subtraction give you? It's not that hard. Anybody?
That's
56 degrees, 36 minutes. That's 45, that's 60. 15 seconds. So anywhere from that declination, that's how far it is above the north celestial equator, to 90. All the stars in here rotate around and around the North Star and never set. So from 56, 36, 15 to 90. Okay? And those 90 degrees north, of course, is the North Star. So anywhere in that frame. Does that make sense? All right, good deal. That's question 14. What range of declinations from 56, 36, 15 to 90 can stars have so that they never set? In other words, they're always above the horizon. All right, now the next questions deal with the planets Mercury and Venus. Now we hadn't, at the time we did this, we really hadn't done much with the planets, but now we've done a little bit, so can someone tell me what's unique about Mercury and Venus, especially compared to Earth? They're what? They are smaller, but so is Mars. Something that's unique about Mercury and Venus relative to Earth. They're what? Closer to the sun. They're the two planets closer to the sun than Earth is. Okay? Now, I can't really use this very well for the sun, but let's just imagine that this is the sun and not Polaris. Okay? It's not the night sky anymore because the sun's there. Okay? Now, if Mercury and Venus are closer to the sun than we are, when we look at the sun, Mercury and Venus is always, I mean, we can't see it in the daylight, but they're always somewhere around the sun compared to where we are. So guess when we're going to see Mercury and Venus most likely, if we see them at all? Just before sunrise or just after sunset. Those are the two times we're going to see them. And that was sort of given away by question number 15. When is Mercury visible in a dark sky? And if you want my honest answer, I'm not certain I've ever seen Mercury. Because two reasons. Number one, Mercury is a small planet. Okay? It's actually just barely bigger than our moon, but our moon's really close to us. Mercury's a long way away. Okay? Very small planet, and it's so stinking close to the sun that just after sunset and just before sunrise, the sky is still pretty bright. You know, it's just beginning to get dark, and Mercury's so tiny, I'm not sure I've ever seen that little speck that would be there. And at least half the time, it's going to set before the sun does, or not come up until after the sun's up. So you're not going to see it half the time ever, okay? No chance of seeing it. So the only time you're going to see it is that little bit. And let's see when they say. Now, this is not this time period. This was a few years ago, but it's not going to be far off. And this is late September, late August. So I'm going to use early September. And it looks like to me early September, Mercury is not visible. Late August. Okay? And all of the month of September, Mercury is not visible. Okay? Now, early October is visible only in the second half of October, and it says visible below Jupiter, and that tells me nothing about when. So it's hard to say. Okay. So you can put down here when is Mercury visible in the dark sky, and just put down for both of those, not visible during the month of August. Okay? How about Venus? When is Venus visible in the dark sky? Now, Venus you will see at least half the time, okay? And because Venus is after the sun and the moon, Venus is typically the next brightest object in the sky. After the sun and the moon, Venus is next brightest. So you will see great Venus, but again, it's going to be just after sunset and just before sunrise. And that's why they call Venus, even though it's not a star, they call it the morning star or the evening star. It's not a star, but it shows up really brightly. First thing you'll see after sunset is usually Venus, if it's visible. And the last star to fade out, and it's not a star, it's a planet, after in the morning will be Venus, okay, if it's visible. So when is Venus visible? Okay, I don't have August, but we'll go with the early September. Very low at dawn near the eastern, north, southeastern horizon. So when is it?
Sunrise?
Say again?
So just before sunrise?
Just before, just before sunrise. So you circle that, just before sunrise. Okay? Now, number 17. Based on what I've just told you, estimate how long each is visible in a dark sky if you can see it. If you can see it. So don't give the answer for Mercury, none, because we know it's not visible right now. But when you can see it, how long do you think it'd be visible? A few minutes, that's it. The maximum would be just a few minutes, because soon either it's going to set at night or the sun's going to come up in the morning. And if you ever see it, it's only going to be for a few minutes, right before sunrise or right after sunset. Okay? How about Venus? Yes. A few hours, maybe. Just a few hours. Not going to be many. Yeah. 1 or 2 at most. I mean, sometimes it'll only be a few minutes, but most of the time it'll be, at max, it'll be just a few hours. So a few minutes for Mercury, a few hours for Venus. Okay? That wraps up the lab. For those who weren't here last time, you can listen to the lab on the YouTube video. Just like I'm recording now, I was recording then. Okay? Now. I'm sorry? If you're finished with it, I'll take it. Okay? Give me something to grade while y'all are taking your tests. Okay? Now, if y'all want to buddy up, the two that weren't here, with people who aren't turning it in today, you can do that because it's a lab. You can work together and y'all can do. But most of it will be out there on YouTube. Okay? Just like today's will be on YouTube. All right. That wraps it up for Lab 1. Okay? So let me get rid of that lab and get the PowerPoint back up. Okay, that PowerPoint, get this one back up. All right, now here's where we left off last time. This is chapter 15 now. Okay, we had already talked about this, I believe, right?
Yes.
Okay, and I think we were just about to talk about what in the world is an astronomical unit. Okay, and for those who have your books, this is on page 379. Very first page of the text in the chapter. Okay? Astronomical unit.
You're talking about what the top bottom.
What's that?
Top of bottom number.
One more time.
The number at the top of the page.
Oh, that's the bottom of the page.
What
379. See, I don't have those little numbers at the top. This is the very first page of text in chapter 15. Okay? You see near the bottom of the second column, it says astronomical units in bold. Yeah, that's where we are. So what is an astronomical unit? That's not Auburn University, by the way, but it's close. Okay? What is that? The average Earth-Sun distance. So when we're talking about stuff in the solar system, rather than talk about how many miles or kilometers they are, and the numbers are huge, we just say the average is 1 astronomical unit, okay? And then we'll reference everything to that. So here they give it in kilometers, 1.5, this on average, 1.5 times 10 to the 8th kilometers. That would be 150, 000, 000, 150 million kilometers. Big number, okay? Now in miles, that would be about 93 million miles. That is 1 astronomical unit, okay? It's really only good for our solar system. You wouldn't use that in measuring from here to the next galaxy. That's in light years. That's a different measurement, much bigger. Okay. Now, so we'll use these later. That's why we're introducing them now, astronomical units. Now, planet classification. I've already sort of hinted at this to you today. We classify planets according to their size. Okay? We already talked about 2 planets, Mercury and Venus, and someone said they're smaller than Earth. You're absolutely right. They are. Venus is almost the same as the Earth, but a little bit smaller. But then Mars, too, is smaller than the Earth. Okay? We talk about their density. Now, that would depend on what their makeup is. A planet that's mostly solid is going to be denser than one that's mostly gas, right? So we'll talk about their densities. We'll also talk about their atmospheres. Number 1, whether they have one or not, and number 2, what their atmospheres are like. So we'll talk about several classifications such as that. So let's get to the first classification, which is sort of neither of these, but a little bit of a couple of these, and these are the terrestrial planets as opposed to the giant planets. The terrestrial means rocky planets, high density, the rocky planets. Generally small size, the rocky planets, okay? And these are the 4 interior planets. Now, the reason I say interior, they're inside the asteroid belt. Inside the asteroid belt. And they are Mercury, Venus, Earth, and Mars. All 4 of those planets are mostly rock. Now, sure, the Earth has a lot of water on its surface, but it's just on its surface. Underneath the water is rock, okay? Even the deepest ocean, underneath that is rock, okay? So we're one of the terrestrial planets. Now, we're mostly rocky materials, mostly. We have some water coming up. And the most predominant material is iron, followed by nickel. So nickel and iron. Now, if any of you had already had Physical Science 112, which I don't think any of you have, you were in the, or you were in the math class with me, okay? You would have realized that iron and nickel are 2 of the 3 magnetic materials, naturally occurring magnetic materials. Iron, nickel, and cobalt are the only 3 naturally occurring magnetic materials. You'll never find a magnet that doesn't have iron, nickel, or cobalt in it. Ever. Okay. So here are 2 of the 2 most prevalent elements on the terrestrial planets are iron and nickel, which are 2 of the 3 magnetic materials. Interesting. Which means they're probably all somewhat magnetic, as in having poles. Okay. Now, outside the asteroid belt, after Mars is this asteroid belt, this bunch of just rocks floating around out there. Okay, and outside that we have the 4 gas giants. They just say giants here, but they're usually called gas giants. Jupiter, the far biggest planet we have. Okay, followed by Saturn, which is really big too, and Uranus and Neptune, not quite as big as Saturn or Jupiter, but about the same size. Okay, those are our gas giants. Now, for those of you who have been following the news, I'd say over the last few years, if you followed any astronomical news, you will probably know or have heard that they are really convinced there may be another planet or two beyond Neptune. Okay? Not Pluto. We've talked about that before, but that there are a couple of more potential planets out there.
So, between Neptune and Pluto, or after,
Okay, yeah, I'll get to that. Let me get him here. This is, goodness, I can't find you. Sarah, Matthew, Darren, right? Okay. And Zachary.
Yes, sir.
Okay. All right. I think Sarah's on a volleyball trip. Kiara, I don't know where she is. She's not in yet. Okay. And Cerenthia is not here. Okay, I think that's everyone accounted for. Well, not here, but okay. All right. Now, let's look at those gas giants. The terrestrial, the rocky planets are mostly iron and nickel. The gas giants are mostly gas, hydrogen, helium, with some methane, which I found pretty interesting, methane there. Because I think of methane as an organic gas. Carbon and 4 hydrogens. And you think, how in the world is that out there on those gas giants that are so cold, can't possibly support life? Where is the methane coming from? Methane seems to be ubiquitous through the universe. It's out there. Interesting. Well, carbon's out there, so maybe it's not too. No. Remember, we already talked about, and it wasn't on this slide, it was an earlier slide. Pluto is no longer considered a planet, but it's a dwarf planet. Now, your question was, where are these other 2 planets, or 1 or 2 planets they think are out there? Way beyond Pluto and Neptune. The thing about Pluto, if you look at it in one sense, it looks a lot more like the terrestrial planet. It's rocky, okay? But it's out there with the gas giants, so that's one thing that's incongruous about it. The other thing is, these 8 planets we're talking about here all fall within the disk that's made up of the solar system. The sun and the 8 planets and the asteroid belt and all that are in a disk, whereas Pluto is like this. Now, they're all a little bit off, not exactly flat, but Pluto is like this, like 17 degrees, and the rest of them are much over 5 or 6 degrees out of alignment. So it's way off. And not only that, but Pluto is in a very elliptical orbit. All the planets are in slightly elliptical orbits, but they almost look circular. They're just a little bit elliptical. Pluto, nowhere close. So sometimes Pluto is actually closer to the sun than Neptune when it's on the short part of its ellipse. But most of the time, it's way out there. Now, these other 2 planets, if they're out there, and they think they are probably beyond Pluto's farthest reach. Okay? Don't know that for sure, but that's what the guess is. And we'll talk about those distances later. Yes? Okay, I can answer a little bit about that.
What's the exact definition of dwarf planet?
What's the exact definition of a dwarf planet? A fairly large blob out there that's not a planet. I don't know what the official definition is, but all those things are taken into play. The size, they're smaller. Pluto is smaller than our moon, and smaller than several of the moons of Jupiter, several of the moons of Saturn. It's not big enough to be a planet. Okay? That's one thing. It's out of whack as far as its orbit. Okay? Now, some of the other dwarf planets are in nice orbits, but Pluto's not. And it's also very elliptical. So, in 2 ways, its orbit is strange. But it just doesn't fit all the criteria of a planet. It was given somewhere in the book. Let me see if I can find the... Here is their definition of a planet. To be a classical planet, an object must be, and this is on page 379, an object must be orbiting the sun, well, all of them are, nearly spherical, and Pluto is more out of spherical shape than the others, large enough to clear all matter from its orbital zone. And I'm not absolutely certain what that means, okay, but Pluto I don't think does it, okay. I think what it means is big enough so that if anything's in that, it's going to attract it to it, and it's either going to burn up or crash into it or something like that. And Pluto, I think, it just doesn't fit, okay? A dwarf planet is defined as an object that is orbiting the sun, just like planets, is sufficiently massive to gravitationally reshape itself into a sphere, pretty much like a sphere, but has not cleared matter from its orbital zone and is not a satellite. It's not the satellite of something else, like Titan. Titan fits everything else, but it's a satellite of Saturn. Ganymede is a satellite of Jupiter, and our moon is a satellite of Earth. So that's what it takes. Okay. Now, we already talked on the last slide or so ago what the other dwarf planets are. Ceres, that's an asteroid. It's one of the bigger asteroids. It's big enough to be almost spherical, okay? Most of the asteroids are small and they're odd shaped. Ceres is big enough to be, okay. And the other three are Eris, Makemake, and Haumea. They're all on page 379. All right. Now, again, pretty picture, nowhere close to reality in many ways. The relative sizes are nice. Mercury's the smallest planet. Okay? They are listing Pluto as if it's a planet. It's not. But it's much smaller than even Mercury. Okay? Venus, Earth, and we do look bluish from outer space. Mars is a reddish colored planet, much smaller than Earth or Venus. Venus almost the same size as Earth, just a little bit smaller. Mars is considerably smaller than Earth, but considerably larger than Mercury. Then you have the asteroid belts. And somewhere in there is Ceres, which would be about the size of some of these moons. But it doesn't specify it here. Okay? Then you have the gas giants. And these are enormous compared to these four terrestrial planets. These are the terrestrial planets, these are the gas giants. They never line up like this. This is just a pretty picture. But the relative sizes are about right, okay? Except for the sun. If the sun was this size, it would be huge and everything else would be somewhere out there past max, you know? So the relative distances aren't quite right either. Inside here, they're not too bad, but outside here, they're way off. Because we'll talk about every time you get one of these out here, the next one is half again farther away. So there's nowhere these are that close together. And so you're getting out. And that's why those next two planets, because these are already so far out here, the next one is half again further out there. It may be that just during the time that man has lived on Earth, these haven't even been above the horizon. They're somewhere so far out and far away that we can't even see them. And maybe one of these days one of them will rise, but it's going to be so incredibly tiny looking because it's so far from the sun, it's not going to reflect much, that you're going to have a powerful, powerful telescope to see it. Our best bet is something like the Hubble Space Telescope, or the next best one they put out there. So, other thing that's sort of okay about this, no moon around Mercury, no moon around Venus, one moon around Earth, and it's one of the larger moons in the solar system. Not as large as Titan around Saturn or the four big ones around Jupiter, four biggest ones around Jupiter, but it's a good-sized moon. There's two little specks around Mars. I am guessing they were asteroids that Mars got within their gravitational field. There's tons of them. They don't even have them all here for Jupiter. Probably upwards 50 or more. Okay, probably around 30 or so around 20 to 30 around Saturn. Teens around Uranus, and probably several around Neptune as well. Actually, Pluto does have at least one moon. It's a tiny chunk of rock, but Pluto is so tiny they almost revolve around each other. The moon is a little smaller than Pluto, but not significantly so. They actually are sort of like they're dancing with each other. Pluto's not moving like the other. They showed it like this. They never line up this way, but at least to get relative sizes, that's not a bad shot. It's just ridiculous. I mean, that's hard. Okay. Now, as I said before, the examples that are in the text, it's sort of like someone thought, we need some examples here, we'll throw something in. They're not necessary for your understanding of anything, but it's sort of interesting sometimes. How long would it take to travel the average distance between the sun and Earth at a typical jet airplane speed of about 1,000 kilometers per hour, using the equation from section 2.2, which of course was in a chapter we didn't do? Well, so 1,000 kilometers per hour, we see here that the astronomical distance is 150 million kilometers. So divide 150 million by 1,000. Basically what it does is knock off 3 zeros. So that would be 150,000 hours. Okay? And 150,000 hours would be 15,000 hours, I'm sorry. They don't have it right. I think it's 150,000. That's going to be, they say, 62 days. Okay? In reality, not going to do that anyway. If you ever got even close to the sun, it's going to burn up and it's going to be pulled into sucked into the sun. So not going to go there anyway. Interplanetary space probes travel about 7.3 kilometers per second. How far could it travel in a year? And you can go through and do the math, but it would be about 2.3 times 10 to the 8 kilometers. And that's just barely one. Their numbers aren't making sense. Yeah, I guess that, okay. So it basically would almost get to the sun, or get past the sun and start coming back again, is how far it would go in a year. So it's sort of crazy questions, and they're not really all that useful. I'll try not to bring them up unless I get something useful. Okay, so let's start looking at the planets. Now, I wish they showed this earlier. It seems like the slide we need to see is going to be late, okay, if they show it at all. The slide you need to look at, and it wouldn't be a very good slide either because the print's so small, but if you have a book, on page 381 in the book is this table, Properties of the Planets. So it has the 8 planets listed here, okay, and it has these various properties. So the average distance from the sun, they do give it in kilometers, but they give it in astronomical units. So that's what we're going to pay attention to, is astronomical units. Okay, and we're going to start with Mercury, so we'll come back and do that in a second. The next thing is inclination to the ecliptic. The ecliptic is the sun's path, okay? Earth path around the sun, okay? And then the inclination would be how many degrees off dead center that is. And you'll see it's not very many. All of them are less than, well, the closest one is Mercury, 7 degrees off, but that's just because it's so close to the sun. The next is Venus, which is also close to the 3.4 degrees, and all the rest of them are less than 3 degrees off. Of course, Earth is listed as 0 because that's how we define the ecliptic. But see, they're all within a pretty narrow band. Okay? The orbital period, we're going to use Earth years there, and you see the closer you are to the sun, the shorter the period, and the farther you are from the sun, the longer the period, because it takes longer to get around. So if you look out there at Neptune, which is 165 years to go around the sun once, okay? And you see that's about twice as long as it was for Uranus. So if there is another sun, a planet out there, it's going to be probably in the neighborhood of 350 years to go around the sun once. And guess what? We haven't been looking for it, but for maybe 15 years. So if it's somewhere on the other side of the sun where it ain't possible for us to see it, it's going to take another 100 and some odd years for it to come back close enough for us to see. So there's a real good chance it's never been within sight, okay? Or that it's so faint that we wouldn't see it if it was inside. You can't see Uranus, Neptune, or Pluto with the most powerful binoculars you could find. You're not going to see them. With really strong telescopes, you can see them. But I don't own a telescope. That would be, I couldn't afford a telescope that would be strong enough to see. Okay. Now, the rotational period is something that's really interesting. Some of them spin slowly, some of them spin fast. Okay? 2 of them spin backwards. We'll talk about those later. Okay? The mass, and again, we'll use Earth as a standard, with Earth being 1, then all the rest of them. The other 3 terrestrial planets will be less than 1, and the 4 gas giants will be minimum 15 times bigger than Earth, more massive than Earth. Okay, diameter, again, the 4 terrestrial planets, very small. The 4 gas giants, enormously large. Okay, and they do those in Earth radius as well. And you'll notice the 3 other terrestrial planets are smaller than Earth, with Venus being close to the same. The others are at least 4 times the radius of the Earth. Now, the density are the really interesting. Remember, that's the one we talked about here. Density. The 4 gas giants are very, very dense. Okay, generally about 5 grams per cubic centimeter. Mars is about 4. The others are greater. But guess what the densest planet is? Earth. Earth is the densest planet. You go out to the gas giants, none of them are even half of what the density of Earth is. Much more massive, but low densities, as in less than 2. One in particular, and we'll talk about it later, is actually less dense than water because it's mostly gas. Okay, the atmosphere, we'll talk about those as we go, and then the solar energy received is a ridiculous thing to put because those closer to the sun are going to get lots of solar energy, farther away from the sun, almost none. If you look at Neptune, Mercury 13.4, I won't even give the units. Mercury 0.002, okay? It's so far away, it's not going to get much thing from the sun. Okay, so now let's look at Mercury. Mercury is the innermost planet. We talked about that. It's a highly elliptical orbit, mostly because it's so close, okay? Its average distance, because it's elliptical, sometimes it's further, sometimes it's closer, is about 4/10 one astronomical unit. So if the sun, the edge of the sun is here, and the Earth is there, then Mercury would be right about here, about 4/10, 2/5 of the way between the sun and the Earth. Okay? Really close. Okay? Orbital period in months only takes about 3 months to go around the sun. Okay? We take a year, 12 months. So it's going around the sun because it's a much shorter orbit. Okay? But the interesting thing, its rotational period is almost 2 months. Okay? So therefore, it turns 1.5 times. So it has 1.5 days in its year. Okay? It seems sort of bizarre, but it is. Its year, you might say, is 3 months, but its day is...
So it has 1 day.
Is 1.5 days, about 1.5 days, because this is 2 months and that's 3 months. So, but who cares? No one lives there anyway. Okay, you couldn't possibly. Okay, and as we said at the end of the last lab, visibly shortly after sunset, if it's visible at all, or shortly before sunrise, just a number of minutes would be about it. Okay, now. I wish they had put these in different order. No atmosphere. No atmosphere at all. Yes?
Like, I understand, like, I got a question, like, the reason why Mercury is the smallest planet because it was too close to the sun.
That's not why it's the smallest, it just happens to be the smallest planet. Pluto, when it was a planet, was smaller than Earth, and it was farthest from the sun. But, so you can't gauge by that. Mars is smaller than Earth, but it's further from the sun. So the distance from the sun doesn't correlate too closely with the size. But this thing of having no atmosphere, that's probably related to being close to the sun. If you think about this, remember, and we'll talk about this a little later in this chapter, the planets were formed about the time that the sun was exploding and coming back together, throwing matter out and then sucking it back in and stuff like this. And more than likely, some of those explosions actually blew away whatever atmosphere Mercury had. Okay? If it had any, it got blown away by all those explosions and stuff. When the sun was in its protostar phase, when it was just becoming a star and the nuclear fusion was just beginning to happen, blowing up and then sucking things back in. It was very unstable there for a while. That's probably when Mercury lost its atmosphere. And because it's lost its atmosphere, it's been peppered with all sorts of junk, meteors, and all sorts of things. Because guess what? They all get sucked in toward the sun too, and Mercury just happens to be close to bang, 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 okay? Now the Earth doesn't get hit by many meteors because most of them burn up in our atmosphere. And that's what we call the meteor showers. Shooting stars, falling stars. Those are meteors burning up in our atmosphere. There's no atmosphere on Mercury, so they don't burn up, they crash into the planet. So it's highly, highly cratered. And it is the smallest planet. I was right, it is the smallest planet, and it's closest to the sun, but those aren't necessarily go hand in glove. Okay? Now here is a gross illustration of what we mean by being visible just very shortly. Okay? If this is Earth, so say we're on the moon, and we're looking over the edge of the Earth, and the sun is either just going down or coming up, you can't tell which. Mercury, and this is exaggerated because the orbit is much closer than what it shows here. When Mercury is closest to the Earth, it's almost none of it being lit because the lit side is toward the sun. So you just have a sliver of it. And that's hard to see because it's so tiny to begin with. Up here, it's, average distance from the Earth, but it's only half of it lit. When it's all lit, it's on the other side of the sun, and it's hardly visible. I mean, it's so tiny. It's over there. And then most of the time, it's over here, or at least half the time, it's in this part of the orbit, and that's below the horizon. So at least half the time, there's no chance of ever seeing it because it's below the horizon. And even when it's above the horizon, it's barely lit, or so far away it's hard to see. So, and guess what? This would only be a few seconds before and after sunrise to see it even then. This would be the longest time you'd be able to see, but it's only half lit because the side that's facing the sun, that's only half you see. So that is a gross exaggeration of Mercury's orbit compared to this Earth's radius, but it tells you why. It's only a few minutes at most that you would ever be able to see it. Because once that sun's up, no way you'll see it. Okay. Or just before. You have to wait till the sun goes down. In other words, this is the case when you ever be able to see it. The sun actually has to fall beneath the horizon of the Earth, and then you have just a few seconds to see it here before it's dragged down, or a few seconds here before, it's dragged down. You have maybe a few minutes to see it out here. That's all, and it's hard to see. Okay. Absolutely no atmosphere, so it's been bombarded with space junk for its whole life. Highly cratered. So here's a picture of it. Actually, it's a composite picture taken by several passes of one of the spacecraft. I don't remember which one. And you see it's just got craters everywhere. Just everywhere. All over. Pitted. Okay? But you see it is spherical. It's big enough to be spherical in shape. It's a rocky planet. Okay? A terrestrial planet. Pretty small though. No atmosphere. No fuzz around here that would indicate any atmosphere at all. Okay. Any questions on Mercury? Tiny planet. Absolutely no atmosphere. About 2/5 of the way between the sun and Earth. That's where it's found. Hardly visible anytime. Very short orbital period, but a very long rotational period. We rotate once in 24 hours. It's once in 2 months. So it's really spinning slowly, but orbiting quickly. Okay? Strange, but true. All right, Venus. Many people call Venus our sister planet.
I just know the fact that Venus is named after a goddess of love.
Yes, exactly. Okay? But I sure wouldn't love to be there. Okay? And you'll see why. So its orbital distance is about 2/3 of the way between the sun and the Earth. So if the sun was here and the Earth was here, Venus is going to be somewhere about here. Okay? So it's the closest thing to us other than the moon. Okay? That's why it's so bright in the sky when you see it. That's why we call it the morning and evening star. The first star you see, or the first bright thing you see after the sun sets, is probably Venus. And the last bright thing you see before the sun rises is probably Venus. Makes it the morning star, the evening star, and it's really not a star. It's a planet. It does also exhibit phases, just like our moon. But frankly, when I look at it with my naked eye, it's just a point of light, so I can't pick out a phase. If you had a good set of binoculars or a good telescope, then you'll see that it has phases a lot like we saw. I'm coming back to it. A lot like we saw here. You get to see slivers sometime. You'll be half of Venus sometime, full Venus. Greatly magnified over Mercury. Okay. All right. Now, here is one of the strangest things, just about the strangest thing about Venus. Its rotational motion is opposite its orbital motion. All the planets go around the sun in the same direction. All of them. Everything goes around the same direction, but Venus spins backwards. Okay? Now, that's part of it. Here's the second part of that same picture that's really strange. Its day, in other words, its orbital spin, it takes longer for it to go around once than it does to go around the sun once. So its day is longer than its year, okay? And its day, the sun rises in the west and sets in the east because it's spinning backwards. But it takes more than one trip around for that to happen, so yuck, it doesn't make any sense, okay? Now, on one of our trips to the planetarium at Stanford University, which we hope to take again this year, the guy there said that there's a lot of speculation that Venus may have been hit by something like a huge asteroid or something else, and that's what knocked its its spin backwards. It actually brought it to a stop and started spinning in the other direction. That's why it spins so slowly, because it's spinning backwards but awfully slowly. Okay? Now, if you go to the table that we had there, you'll see the orbital period for Venus was 6/10 of a year, so about 3/5 of a year, but its rotational period is 243 days. But it's a minus, meaning it's spinning backwards, and that's about, more than 2/3 of a year. So 3/5 of a year is its orbital period, its year, you might say, whereas its day is more than 2/3 of an Earth year. So it's spinning slower than it takes to go around the sun. Okay? Now, because it's the closest planet to us, planet now, not moon, but planet to us, it's been visited by numerous probes, many, many probes. And they have taken pictures, they've measured atmosphere, they've measured temperature, they've measured all kinds of things about it. Now, here's the deal. Its atmosphere is mostly carbon dioxide. What do we consider the carbon dioxide in our atmosphere? This is just to see if you've been reading press. What do we call carbon dioxide in our atmosphere? We tend to have more of it now than we did probably 100, 200 years ago. What's that? It's what we breathe out, exactly. It's the byproduct of combustion. We breathe in oxygen, we burn hydrocarbons and carbohydrates, and we expel carbon dioxide. Because the combustion process, and the reason we have a temperature, 98.6 or whatever, is because we are slow burners, okay? We are consuming hydrocarbons and carbohydrates. We're metabolizing them in our system, and it's giving off heat. And it also gives off carbon dioxide. Okay? Now, I use that term burning. What have we been doing in the last few hundred years?
Missing of Earth.
Say again?
Missing of Earth.
Yes, how so?
I believe you're trying to go with the gas chemicals that we release into the atmosphere, as far as from big planets.
Say that again? Okay, the fires. Okay, you mean like the forest fires and the wildfires? Yeah, but those have probably happened throughout Earth's history. Okay? Now, they may be faster and hotter and more of them now, but what have we also been doing? We have been, say again?
We release carbon monoxide
and dioxide. And the reason we're doing that is because we've been excavating coal, oil, natural gas,
getting rid of a lot of trees.
And we've been burning tropical rainforests. And every bit of that is oxidizing or putting more carbon dioxide into the atmosphere than the trees. See, those trees are living out there because they're taking carbon dioxide out of the atmosphere and putting oxygen back in. That's why we can live. Guess what? If they weren't doing that, we don't exist. We would not have enough oxygen to breathe. Because of the trees out there taking the carbon dioxide out of the atmosphere and releasing oxygen into it, that's what we do. Because, see, oxygen is one of the most reactive gases and elements out there. It's going to combine with something that leaves release it as pure oxygen. And we breathe it before it reacts with anything else. So, thank you, trees, okay? Grasses, plants, green plants all over. That's what's doing it for us. Now, what we've been doing, okay, over millennia, plants have died, especially in boggy, wet areas, and their leaf mulch, and animals have died. They've been piled up and piled up and piled up and piled up, stuff on top, and it gets compressed, and actually all that organic matter, the water gets squeezed out, and then ultimately it goes to something they call lignite, and that becomes coal, and later, after more chemical reactions and things like this, and heat and pressure and stuff, it becomes petroleum or natural gas. Okay? That's been accumulating. The Earth's been around maybe 11 billion years. It's been accumulating probably at least 9 or 10 billion years. Okay? That's where all that stuff came from. Maybe not quite that long. Whenever it started, it's been doing that long. Okay? And what we've been doing since the Industrial Revolution, we started burning coal. People were already burning coal to heat their houses and things like this. But a lot of people use wood, which is renewable. It's here today, grows again, grows again. That's doable. But since the Industrial Revolution, we've been burning coal, we've been burning petroleum, we've been burning natural gas, we've been burning anything hydrocarbon we can get our paws onto. And some of that stuff was made billions and millions of years ago. And we've been consuming it as fast as we can get it out of the ground, releasing that carbon dioxide into the atmosphere. And we call it carbon dioxide, this is what I originally was saying, a greenhouse gas. What that means, it traps more heat than it lets to go out.
And that's why Venus is so hot.
And that's why what?
Venus is so hot.
And that's exactly right, why Venus is so hot. Because its atmosphere is mostly carbon dioxide. It is a thick, dense atmosphere, mostly of carbon dioxide, but it does have plenty of sulfuric acid, hydrochloric acid, methane. It has all these things in it. It's a miserable place. Planet of love, I wouldn't love to go there, okay? Or named after the goddess of love. Wouldn't want to go there because its temperature is so hot. Now this is incredible. Remember, Mercury's back here at 4/10, two-thirds of the way from the sun to Earth, whereas Venus is over here at 7/10. You know, less than half the distance between Mercury and Earth, you'll find Venus. So it's more than twice as far from the sun as Mercury. Now, the side of Mercury that's facing the sun is hot. It is incredibly, incredibly hot. But the backside of Mercury, because it has absolutely no atmosphere, the side away from the sun is incredibly, incredibly cold because it doesn't get any direct radiation from the sun. It's exposed to outer space, basically. So the average temperature of Mercury is hot. Yeah, sure, it's hot. But the average temperature of Venus is even hotter, even though it's more than twice as far from the sun. And why? Because that carbon dioxide atmosphere traps the heat and it doesn't go. Whereas the backside of Mercury loses that heat immediately. When the sun sets on Mercury, there goes the heat. Where the sun sets on Venus, it hardly changes at all because that atmosphere traps it in there. High temperatures, high pressures. Now, the surface of Venus is mostly flat, but is varied. It probably doesn't have many craters because its atmosphere is so dense, any meteorites that are coming in get burned up like crazy, far more than the Earth would be. But it is varied in that it has mountains and volcanoes and other things, a lot like Earth does. Okay? So, other than that, it's mostly flat. Not a hospitable place to be. Nowhere to go for a honeymoon. No, hang that one up, okay? You don't want to go to Venus. All right. Now, when it said, and let me do a timeout here. I should have said it earlier. For two new people who are here, what we do, well, I decided to do, and I think it works well, is whatever we're doing in the day, if we're having theory type stuff, going over stuff in the book, we have it at the beginning. If we're going to have a lab, it's either at the end or near the end. Therefore, when you finish the lab, if it's the end of the day, you get to go home. Okay? Last time we didn't quite finish, so we were here the whole time. That's the longest lab we're going to have. Okay? But when we do have a test, that is the last 30 minutes of the day. And the reason for that is that if you finish the test early, you can go. You don't have to sit around and wait for everybody else to finish, and then we pick up and go back to class again. No, you don't have to. When you finish, you can go. And if we don't have a lab that day, which we probably won't today, then when you finish, you go. If we do have a lab but not a test, when you finish the lab, you can go. So I do the things that you're doing independently or individually. That's at the end of the day, so when you finish, you can go. You don't have to hang around, and then we have class later. So that's why we're in Chapter 15 now, but the test for Chapter 14 will be the last 30 minutes of the day. So that's what's going on. And like I said, I don't think we're going to finish this in time for a lab today. Pretty certain of it. This is our table 15.2, and it's their table 15.2. Also, in our book, it's greenish colored. And our book goes a little bit further than this one does. This one ends in 1989, and ours goes to 2007. Okay? Only two more, but it's two more out there. Like it said here, visited by numerous space probes. Here's a maybe close to complete listing of those space probes. And like I said, there's two more listed here, both one in 2006 and one in 2007. Okay? And what you might notice is USSR, y'all remember what that was, right?
Yeah, that's the Soviet Union.
Soviet Union, Union of Soviet Socialist Republics. Exactly. They went to Venus more than we did. It was closer. They got the jump on us. And rather than competing with them, we said, okay, you went there, we'll go to Mars, okay? A little bit further away. When we show the same thing from Mars, you'll see we're more and they're less, okay? But, now this is just sort of a generalization. Generally, we've cooperated fairly well. We were competing for getting up there first. They beat us, but we got to the moon first. We always have been competing, but in general, we share results pretty much, I think. And today, we're even better. If you'll notice the last two in your book, the one in 2006, the owner was not USSR, not US, but ESA. What in the world is ESA? European Space Authority or Agency. So they are in the picture. And many of the things up there now are international. In fact, Soviet Union had the first space station. Okay? And after a while, we were helping haul them stuff to the space station, their space station, and we were sharing and stuff. Right now, on our, it's not even ours, it's the International Space Station. They contributed, Europe contributed, Japan contributed, all sorts of countries contributed. We did probably most of it. It was built by our shuttle fleet. That's the only device big enough to haul those pieces up there. So we hauled them up and brought things back and various things. And much of the space station is inhabited by both cosmonauts and astronauts. And it's been that way for years. So we really had a pretty good history of cooperation. So they sent us pictures, we sent them pictures. Okay? You'll see flybys here. They had one that crashed. This one crashed. That sounds like an accident. This one impacted. It sounded like they meant to go down and get data as far as they could. And you can see so others impacted in various things. And you see some of these are flybys. This one, see, was from the U.S. We flew by Venus so we could get to Mercury and take pictures. And that's where the pictures came from Mercury, and the pictures will be from Venus as well. Okay? They have, USSR did some landers and orbiters, and I can guarantee you the landers didn't last long, okay? Because it's so hot, it's so inhospitable, probably so acidic and just really bad that you can't leave anything there for very long. It's not going to last, okay? So anyway, here are some. These are, you see the Veneras are the Soviet Union. They were meant for Venus. The Mariner was meant for, actually for Mars. After it went to Venus and Mercury, it was going to try to go to Mars, okay? And then others have all these names, okay? Those are the numerous visits. Closest planet, no wonder it got visited a lot, okay? Now here is a picture, and I don't know whose picture this is from, whether it's from, we did, I think, land something. Did we land something on it? It doesn't show we landed anything, so this could be from a Soviet when they actually went down into and either crashed or impacted and took these pictures as it went. This looks like a huge volcanic mountain, okay? And this looks like lava flows, either coming off that mountain or coming from somewhere else. It's not a very pretty picture. I mean, the colors are great, but you don't want to be there. It is hot and inhospitable. You wouldn't be able to breathe. Carbon dioxide, there's just nothing. Okay. So, there's Venus. Oh, we're skipping Earth, aren't we? Next chapter is Earth-Moon system, so we're going to talk about Earth in the next chapter. But the table that we are referring to, that has a lot of stuff in it about Earth as well. So now we move to Mars. Now this is where things really pick up. Okay? Remember I said Mercury is about 2/5 of the distance between Earth and the Sun. Okay, 2/5. Venus was about 7/10, so it was more than twice as far. Now Venus and Earth are fairly close together, 3/10 of the thing, so they're fairly close. But once you get Earth, Mars is 1.5 times. So you see, if this is Sun to Earth, Mars is in out here, way further than the closest here, 1.5 times as far. Okay, so about 1.5 astronomical units. Okay, geologically active regions. That means they have had volcanoes. They're mostly inactive now, but they have had active regions before. Canyons? What in the world is a canyon? Make some guess. So, like the Grand Canyon. What form of the Grand Canyon?
Water.
Water! Wait a minute. Does that mean that sometime there was water on Mars?
Yes, and the sun, I think the flares that I know the flares it produced had burnt the atmosphere and dried out Mars. It was like Earth, but God said not today, and took away the water in the atmosphere.
Okay.
It also used to be very active with the volcano system, and it has the biggest volcano in our solar system.
Oh wow, very good.
And the Grand Canyons on there is way huge than ours. Like ours can fit perfectly and still have room to move around.
Right. And if you think about it, the size of Mars much smaller than Earth, and yet it has the tallest volcano in the solar system, which is really interesting. But the fact that it had canyons, now you would think a solar flare that reached Mars that was 1.5 times the distance from the sun the Earth is, that solar flare had to go by Earth too, didn't it?
The different rotations.
Different rotations and stuff like this. We either dodged the bullet, solar flare bullet, or else, I don't know.
The magnetic field is stronger than Mars. It barely had one. That's why it perished.
What's that now?
The thing that protects us from the solar flares, Mars had one, but it was way weaker.
Yeah, and it got blown away more than likely. So yeah, there's all. Excuse me.
It's tight.
Are y'all awake yet? Okay, I have to do that every now and then just to make sure everybody's awake. Okay, I forgot to get my pen out. My watch out. I broke my pen on it. So why is it 3 o'clock? Okay. All right. So, Mars is probably, because it's geologically active regions, at least in the past, a lot like the Earth. Canyons, meaning possibly water at one time, a lot like the Earth. Terrace plateaus near the poles, and this is where they think the water resides now, but in ice, but beneath the surface. There are flat regions pitted with craters, and here again, thin atmosphere. Thin atmosphere, therefore lots of craters, okay? Because they don't have anything to absorb the energy from those falling objects. Now, look at its atmosphere, mostly CO2. So the planet inside of us, mostly CO2. The planet outside of us, mostly CO2. Why did we wind up with, what's our atmosphere mostly comprised of? Yeah, nitrogen mostly, close to 80% nitrogen and close to 20% oxygen. There's other stuff in it, but that's the thing. Why did we wind up with that? Well, part of the reasons is our green plants take the CO2 and release the oxygen. That's why we have more oxygen.
Those organisms that's in many of the beaches on Earth, they release oxygen. I forgot the name of them, but they look like rocks, but they're really not. They're alive. They produce oxygen too, because they absorb stuff out of the atmosphere.
And what are you talking about there?
I don't know the name of them, but NASA talks about it. It's like
on
these
Earth?
organisms on Earth
okay.
that also produce oxygen.
Okay, yeah, okay. The organisms, okay, that's what I was trying to get. There are two types of, maybe more, but at least two types of what we call microorganisms. Some are aerobic and some are anaerobic, okay? Now what that means is the aerobic means they require oxygen to live, and just like we do, and then they breathe out usually carbon dioxide. Okay, the anaerobic, they don't require oxygen to live. They get the oxygen from other sources. Okay, they require oxygen to live, but they don't do it by breathing. They get it from other chemicals and stuff. In fact, in your gut, you have aerobic microorganisms and anaerobic, and that's everywhere pretty much. So there are organisms that do potentially release oxygen like you were talking about. Okay, but the interesting thing is if we didn't have the green plants, we would be mostly carbon dioxide. We still have that nitrogen. We're the only planet in the solar system that has much nitrogen. Why? I don't know. I just said let there be life here. I don't know, but that we have nitrogen, the others don't. But if it weren't for that, the oxygen would not be oxygen, it'd be carbon dioxide. Okay, that's where it'd be. See, every carbon dioxide has an O2 in it. Okay, so thank you, Green Planets. Okay, there's strong evidence for liquid water in the past, as in those canyons and things, and there's also things like this. And to me, this picture doesn't prove a thing. Okay, but the people who know what they're talking about, they see the shapes on these rocks, and it indicates something has worn them differently on one side from the other side, and usually that means water. So that's what that picture is trying to show, but I can't tell you exactly how that's the case, but that is the case. Strong evidence for liquid water in the past. Does that mean there was ever life there? No, it doesn't. But
bacteria and stuff for this.
Well, yeah, there could be. They still haven't found any. But if there wasn't water, there couldn't possibly be life. Not as we know it. Since there is water, there potentially could have been life. Okay? So, no evidence so far that they found that there is or has been life, but at least they think there was water, which made it so it could have been. Now, this, I think, this is not some extraterrestrial stuff, or actually it was. It was us. We landed there and left that mark there. Okay, but this is what the surface of Mars looks like. It's a red planet. And the reason it's red is mostly iron oxide. Rust, that's what makes up. Because remember, most of the terrestrial planets were iron with some nickel. So yeah, sure enough, most of the surface of Mars is probably high in iron content. Okay? Now, numerous space probes again. Let's see if they're going to show that. No, they don't. But in the book, if you go to Mars, you'll see table 15.3, completed spacecraft missions to Mars. Okay? And most of these have Mariner in the name, except the USSR just calls theirs Mars 2, 3, 4, 5, 6 stuff. But you see, we outdid them a little bit on Mars. They outdid us on Venus. We outdid them on Mars. Okay. And maybe that was by understanding and design. I don't know. Now, there is a pretty good picture, representative picture. And this would be a lot like the space objects in perspective picture that you look at. Here is Mercury. There's Venus, almost as big as Earth. Not as dense as Earth, but almost as big as Earth. Earth with a huge moon. There's Mars, and by the way, this moon is not that much smaller than Mercury, our moon. And then here's Mars, much smaller than Earth or Venus, not as small as Mercury, however. Its little moons are like this, and that's what most planets' moons are like. Tiny little objects going around them. Our moon is exceptionally big for the size of our planet. And there are other things, and we'll talk about this in the next chapter too. Okay? Now, there's some other examples here. I'm not going to go into great detail here. If the noontime temperature surface of Mars can reach as high as 20 degrees Celsius, that's basically room temperature. Okay? Is that warmer or colder than a typical room temperature of 72 degrees Fahrenheit? Well, yeah, it's a little cooler. 20 degrees Celsius is about 68 Fahrenheit. 72 is a little bit warmer. Okay? Mars' coldest temperature is around minus 140 degrees Celsius. What is that in Fahrenheit? Minus 220 Fahrenheit. Ain't no life that we know going to live there at night. Okay? So, just to get an idea. All right. And on page 386, at the top of the page, there's something they call a case study. These are usually pretty well worth your read. Basically, this is saying, is it worth the cost? And you hear people say this all the time. Man, if we can afford to send somebody to the moon, how many people could we feed here on Earth? Well, yeah, that is a good, valid argument and discussion. But we do get a lot of benefit from studying and understanding what's going on out there back here. You know, we'll be saying the same thing about Mars because, frankly, what NASA's talking about now, you know, we've been to the moon, we've done stuff on the moon, we've sent things to Mars. We've never been, in fact, we've never been anywhere except the moon outside of the Earth. That's it. Just into space around the Earth, and we've been to the moon and back. We haven't really ventured very far, but there is concern and some planning to actually send somebody as far as Mars. You don't want to send them to Venus. That's just way too hot. Yeah.
Why do we not try to discover more about our oceans and going to Mars?
Okay.
Still only know 95% of our oceans.
Okay, yeah. That is another really excellent question. And it is broached in both chapters. Why don't we spend more time learning about Earth, as in our oceans, than we do outer space? Well, our oceans are also fairly inhospitable, okay? If you try to go down in the deepest part of the ocean, the pressure is so great, you have to have a craft that can withstand incredible amounts of pressure. In fact, it's only been in the last, I'd say, 10 or 15 years that we actually developed a craft that could go down to the Marianas Trench, okay?
What they need to do is make a camera that can, withhold all that pressure. But we can discover more of the deadly animals. I refuse to get up in the ocean.
Okay, now, that's one thing. It's very high pressure down there. The second thing, it's incredibly cold temperatures down there, okay? Very cold. In the Gulf of Mexico, when they had the Gulf oil spill, what was that, about a decade ago or so? Yeah, something like that. When they had that oil spill, it was about a mile down, and that sounds pretty deep to me.
That was
but
about 10 years ago.
I said about a decade, about 10 years ago, okay? When they did that, it was so cold down there, that was one of the reasons they couldn't get it to stop. They didn't have equipment that could operate in that cold temperatures with that much pressure and be very effective. It took them weeks of all that stuff coming out into the Gulf of Mexico before they could ever figure out a way to get it to stop. So there's a... What's that?
I feel like you can go to outer space and still figure out.
It seems like they could figure out some of those problems as well. And the third one, it's so incredibly dark down there because there is absolutely no light, makes its way past probably, I'm going to guess, about 50 meters. It's so incredibly dark. And even if you have a light, it's so dense down there, it's really hard to see but a little bit. So there are a lot of challenges. I agree. They can't be any greater than the challenges of going into space, but they're kind of the reverse challenges. And yeah, it's a very good question. And many people say, why aren't we? In fact, this is something that concerns me. We are polluting our oceans so badly, we don't even understand what we're doing to them. So we need to be studying them big time just to keep them from dying. And that has happened almost. There are some literally dead spots in some of the oceans that hardly anything's living. And that's scary because that's where all life pretty much came from. Okay. So yeah, excellent questions. Okay. They're talking about the relative gravitational force of Mars compared to Earth. How fast would a rock falling from 60-meter high cliff on Mars be traveling when it hits the Martian surface if the gravity G for Mars is 3.8 meters per second squared, that's the acceleration due to gravity, whereas on Earth it's 9.8 meters per second squared. So we're almost 3 times the acceleration, so the speeds would be much less. Plus, well, then you also don't have much atmosphere, so all sorts of things enter it. How long did it take that to hit the ground? About 5.6 seconds to fall 60 meters. Much faster on Earth. Okay. So there's Mars. In many ways, more of a sister planet than Jupiter is. It's a little more hospitable, much smaller. Many things are not similar, but other things are. So let's go to Jupiter. Whoa. All right. Now, Sun here. 4/10 of an AU is Mercury. 7/10 of an AU is Venus. 1 AU is Earth. 1.5 AU is Mars. 5 AUs is Jupiter. Wait a minute. Why the big gap? What's in that gap?
Is it
The asteroid
yeah,
belt.
the asteroid belt?
That's where the asteroid belt is. Now, many people, astronomers and others, feel like there should have been a planet where the asteroid belt was. That would fit the pattern far better, because if you're gaining half again the distance again, then that would be, when you got to Mars at 1.5 AUs, then somewhere around 2.5 or so, maybe a little further, would be another planet, and then 5 would be Jupiter. That would kind of make sense, okay? But there's not. Now, there's several theories on why not. Jupiter is so incredibly big and such a strong gravitational field, they think that's what kept the asteroid belt from clumping together and being a planet. Jupiter was basically yanked it apart. But we don't know. So about 5 astronomical units from the Sun, way out there. 5 times the distance from Earth to Sun is Sun's Jupiter. The most massive planet, big time. Okay? 318 times the mass of the Earth. Now the mass of the Earth is, of the 4 terrestrial planets, it's the biggest one. Jupiter itself is 318 times more massive than the Earth. It is huge. Okay? And yet it's mostly gas, hydrogen and helium. But it does have a core, an iron silicate core, which is probably not far from being the composition of Earth. So the core of Jupiter is a lot like Earth in composition, anyway. Okay? Okay, good question. No one's been there. Okay.
A camera tried.
No one's been to Earth's core either, you know.
A camera tried, but Jupiter's atmosphere has so many layers that if you go for more pressure than forces, you get crushed.
Right. Okay. There's so much pressure there, that's certainly one thing. But here's the other thing. We can tell the gravitational field of Jupiter, right? Gravitational field is related to how much mass there is. We know its diameter. We know the gas concentration and stuff. Most of it, the only way it to have that much mass is for it to have a solid core. And to get that solid core, knowing that the rest of the universe is mostly the solid material is iron, you have to assume it's iron, okay? With some silicates, because it's not pure iron, because it's not as dense as that would be. So that's their rationale. Now, whether they have any kind of, what do you call it, spectroscopy that they can do on it, I can't imagine that they would, but they may have some sort of backup evidence for that too. I just don't know. But here is the thing, and we'll see this in later chapters. They think that the composition of the meteors and things that you find floating around mirrors what the rest of the planet is. And most of those meteors are iron and iron silicate. So that's why they think it's probably their core. We know it's a lot denser than the gas because we know what the total gravitational field is. So that's our best guess. Good question, though. Okay? Now, here's sort of a description of Jupiter. Later we'll see a similar description of Earth. This will be in the next chapter. And the picture looks fairly similar, but they're very, very, very different. Okay? Now, this iron silicate core we talked about in the middle, it itself is like 10 to 15 times the Earth's mass. So you could get 10 to 15 Earth into that core, the masses into that core. So even the core of Jupiter is 10 to 15 times the mass. The total planet is 318 times the mass. So it's huge. It's huge. Okay. Now, the odds are I think this has to be solid. I mean, but it could be molten. We just don't know. Now, the interesting thing is the next layer here is called, I guess you would say, liquid metallic hydrogen. What? Okay, and that's 35,000 kilometers of liquid metallic hydrogen. Okay? Now, hydrogen to be a liquid has to be awfully, awfully cold. Okay? And to be compressed so that it's almost metallic in nature, that's a lot of pressure too. And pressure usually means heat, but this is liquid, so it has to be incredibly cold. Ooh, I can't even imagine what that's like. Then we have the liquid hydrogen, not metallic in nature, here. And then you have the atmosphere of hydrogen, helium, and ammonia gases. So we call it a gas giant because its outer shell, outer atmosphere is gas, but that's not really very thick. I mean, it may be miles and miles and miles and miles, which seems thick to us, but it's not that thick compared to the rest of it. Then it's liquid hydrogen, which has to be incredibly cold to be liquid hydrogen. And then liquid metallic hydrogen, which means the pressure on it is so great that it's made it more metallic in nature. And then you have an iron silicate. And that iron silicate core alone is 10 to 15 Earth masses. This is one big planet. I mean, and when we get to the planetarium, if we get to go, he'll talk about Jupiter's gravitational field is just, it wreaks havoc on the whole solar system. The sun is much greater, but after the sun, Jupiter is second by a long bit over who's number 3. Okay? Jupiter is massive. Massive, massive, massive. Okay? Here is a picture, actually a picture of Jupiter, and this is basically a picture of his outer atmosphere, which is those gases, iron, methane, hydrogen, hydrogen, helium, and methane. And this is called the Great Red Spot. It's a huge storm that's been raging on the planet Jupiter as long as we've seen the planet Jupiter. It actually seems to be diminishing a little in the last few years. Whether it's going to flare up again, I don't know, but it's called the Great Red Spot. Okay? It's a huge storm in that atmosphere of hydrogen, helium, and methane. It's just been raging forever. Okay? Kind of like a super hurricane, but doesn't get over. Okay? It just keeps raging. Okay? Now, in your book, they show a lot better detail of that Great Red Spot, and I'll let you look at those pictures. The next thing shown here, and why... Oh, wait. Yeah, okay. It has a dynamic atmosphere. That's what I was just talking about. It's always changing, always moving, always mixing. Mostly hydrogen with helium, with ammonia, with methane, and water. Water vapor or water It seems like it would be so cold it couldn't be liquid water, gaseous water, but it has water in its atmosphere. And like I said, the Great Red Spot. Okay, huge storm that's been raging and raging as long as we've had pictures of Jupiter. It has an incredibly large system of varying satellites. Okay, and I haven't seen the latest figure. Let's see if no one knows exactly how many it has. All they say in our text on page 388, Jupiter has tens of moons. That means more than 20 or 30. I think the one number I saw was as many as 50. Okay, maybe even more. Okay, some of the smaller are yet to be discovered. That's why we don't know how many it has, because they only have discovered the biggest one. The four brightest and largest can be seen from Earth with a good pair of binoculars. Now, I've never done that, okay? I've never seen them, but they say with a really good, strong pair of binoculars, you can see the four biggest moons of Jupiter, which to me is incredible, thinking how far away it is, okay? It is 4 times the distance from Sun to Earth. 4 times that distance is the distance from Earth to Jupiter. To be able to see moons from that distance, that's amazing. That is amazing. Okay? That's the 4 biggest moons. And it probably has 50 plus moons around it. Okay, there. Now this is, to me, sort of a weird picture. This is the Great Red Spot. And this is a white cloud, another storm, sort of a counter storm around that. It looks like there's a smaller one here and here and here. So there's all sorts of storms. If you go back to that earlier slide, see, here's the Great Red Spot. Here's that other storm, the white one we just saw. It's much smaller. But why our picture focuses on that and not that, I'm not sure. Okay, but it does. Okay. All right, so that's the edge of the Great Red Spot, that white thing. And I think that's supposed to be one of the coldest surfaces of the atmosphere, where the Great Red Spot may be hottest, or I may have those backwards. Okay? Now, here are the 4 largest moons of Jupiter. They are called the Galilean moons. Why would they name them the Galilean moons? Say again? Yeah, he being Galileo. And think about that, folks. Okay, now Galileo did not invent the telescope. He was from Italy, Pisa, Italy. There was a guy somewhere up in Northern Europe that invented the telescope. Okay? And his telescope was remarkable in that no one had ever invented one before, but it wasn't all that great. I mean, incredible because there had been nothing like it before. Galileo heard about it, heard how he did it, and Galileo proceeded to come up with one that was like many times more powerful. And with his telescope, he was then able to look at Jupiter. And when he looked at Jupiter with his telescope, he could see these 4 moons. And yeah, so he discovered them. They were already there, but he was the first earthling to see those moons. And therefore they're called Galilean moons. Okay? When was that? He preceded Isaac Newton. Okay? He and Isaac Newton were basically the ones who started what we call the modern scientific method. They were the fathers of science, you might say, on the planet. And that's how long ago it was that they discovered these. Now, they say today you can see them with a really powerful binoculars. I've never seen them, but that doesn't mean they can't be seen. Okay, so here are these 4, and these are pictured in NASA's Galileo spacecraft orbiting Jupiter, and they're from Now, they say here left to right, and because the picture we have in our text is lined up like this, but they're the same order. The first one here is EO. I-O, E-O, something like that, okay? That's the first one, upper left. Upper right is Europa, okay? Lower left is Ganymede, and the far right on the lower side is Callisto, okay? Io and Europa are about the size of Earth's moon. Ganymede and Callisto, the bigger ones, slightly larger than Mercury. These two moons of Jupiter are bigger than the smallest planet, okay? These are huge, okay? Slightly larger than Mercury, okay? Now, I don't think they're the four largest in the solar system. I'm pretty sure Titan around second. Second largest. Who's the largest, you know? Who does? Jupiter has it. So it may be Ganymede. It looks like that's the larger. So maybe Ganymede's largest, Titan's number 2, and Callisto's probably number 3. Okay.
Did you know that most of the moons that NASA and them found out back in 2002, 23 of them was found, but only 11 of them have names. Those are 4 of the 11 official moons.
Yeah.
But Jupiter has like 23, according to NASA.
Who, Jupiter does 23?
NASA says it right here.
23 named moons or 23?
No, 23 moons, but only 11
11
of them
right.
became official because they got to meet a requirement of something.
Right. Okay. There are other things orbiting Jupiter that number up as far as 50. Yeah. Right.
That's why they're not named.
Right.
Okay.
And by the way, the picture in our text of Jupiter, a much better picture than what I was talking about. This is from Hubble. The slide set that we have here almost precedes Hubble, so that's why we have some in the book that are actually much better. Okay. Now, we're going to run into something later in this chapter about Jupiter. So we'll come back and see it. In your book, it's hit here. And the slide set is a little bit later. And what happened, okay, and this is why the slide set put it off till later. As I said earlier, the planets are slightly elliptical orbits. They are all ellipses, but they're fairly circular ellipses. They're not circles, but they're closer to being circles than not circles. Okay? Whatever that is. The other things in our solar system are really wild ellipses. For instance, the comets. The comets they come in really close to the sun, and then they go way, way out from the sun. And that's what Pluto's doing more than this other planet. It gets closer than Neptune part of the time, but most of the time it's way out further than Neptune. It's a very elliptical orbit. Well, one of these comets happened to be coming through our atmosphere, through our solar system, and got a little bit too close to Jupiter. That's not a good thing to do and live to tell about it. Because Jupiter has such a strong gravitational field. It's so incredibly massive, it sucked that comet, broke it apart, and pulled it into the thing. And that's what the picture in your book on page 389 shows. A series of flares going up. That's where the pieces of that comet that is no longer, it was the Schumacher-Levy comet, doesn't exist anymore. It got sucked into Jupiter, and it's now part of Jupiter, okay? So it's no longer. We'll see that later on the slide set, but it's not now, Okay. Now, all right. Okay, not quite. All right. Let's move on to Saturn. Okay. Now, catch this, folks. Remember those distances? 0.4 astronomical units for Mercury, 0.7 for Venus, more than twice as far. The only one for Earth, so that Venus and Earth are rather strange. They're too close together almost. 1.5 for Mars. Now we're getting further and further apart. 5 astronomical units for, that's more than 3 times as far from Earth to Mars as it is from Sun to Mars as it is from Sun to Jupiter. I mean, it's way out there. But then, almost twice as far as that, 5 to Jupiter, 9.5 astronomical units to Saturn. So you see they're getting almost double the distance every time to the next planet. That wasn't, it happened between Mercury and Venus, but it didn't happen between Venus and Earth and Mars. But now it's happening in these gas giants. So therefore, that first picture that showed them all in nice little circles, no way. Those are way, way out there. So almost twice as far Saturn is from the Sun as what Jupiter is. And by the way, all the gas giants, Jupiter, Uranus, and Neptune, have little rings around them. Minuscule, hardly noticeable. Saturn, though, has these incredibly beautiful rings. It sets it apart from any other of the planets. Here's something else that sets it apart from the planet. Its density of the entire planet Saturn is less than the density of water. If you had a tub of water big enough, which there isn't, and put Saturn in it, it would float. An entire planet floating in water is 7/10 the density of water. Whereas Jupiter, Uranus, and Neptune, they're about twice the density of water. They would sink. Saturn would not. Very, very, it's the lowest density of any. Which planet had the highest density? Earth! Yes, we're the densest. Does that sound good? And Saturn is the least dense. Okay? The surface is very similar to Jupiter's. That, gaseous outer shell, and then everything is very similar. Now, here they say, Saturn, they think, has about 30 satellites. That's why I'm pretty sure Jupiter is figured to be around 40 to 50. But Titan is the only moon with a substantial atmosphere. And it's, remember, bigger than Mercury. Remember, Mercury has no atmosphere, okay? Mars doesn't have much of an atmosphere. Titan has a substantial atmosphere.
Research Titan.
What's that?
Titan also have water on the surface.
Okay. It's probably ice water, though. It's probably not liquid.
It's rivers of methane.
Okay, and it's liquid methane. Yeah. The liquid that's there would be methane, but it probably does have water ice there. Okay. Oh, it's way cold. It's way, way, way too cold to have liquid water. But it could have liquid methane.
And most of the clouds on Titan covers over the South Pole. That's very cool.
Really? It congregated over the South Pole. That's interesting. It's just so cold the whole thing is. I don't see why it would congregate, but there must be some reason. Okay. Here is one shot of some of those rings. And aren't they beautiful? Okay. They're mostly dust and icy particles. Must have different compositions because they have different colors to them. But it's just an incredibly beautiful phenomenon. Okay? That could be a paper topic, by the way. Analyze, what have we learned about the rings of Saturn? And we've had several probes go up there. The most recent that I recall was the, goodness gracious, it's a hyphenated name. I can't think one of the shows that he showed us at the planetarium focused on that. Cassini-Huygens, that was it. Cassini-Huygens. It was from the European Space Agency. Really studied these rings pretty well. So if you could find that, that might be pretty interesting to you. There is a photo in the book of Uranus, and you see one or a few little rings around it. Nothing like Saturn, but it does have those rings. There's a picture in the text of Saturn with the rings around it, but then you have these other objects that are floating around it that probably are moons. But Titan is way out there. It's in one of the rings, but it's a very faint ring. Okay. So there's Saturn. The important thing to remember, of course, it's rings, but also the fact that it's so low in density. Now, Uranus and Neptune, they are so similar, and we know almost nothing about them except what we studied. But okay, remember this? Jupiter, 5 astronomical units from the Sun. Saturn, 19 and a half, almost twice as much. Uranus, almost twice that. In fact, exactly twice that, about 19 astronomical units. Then Neptune, 30 astronomical units. Now, not quite double. That's where that sort of broke apart. But it's way, 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 way out there. Okay? So that early picture I showed that had those pretty little planets all lined up in a row, it doesn't happen that way. Not going to. The outermost of the giant planets we know about. There is some idea that there may be one or more out there beyond them, but they haven't been discovered yet. They see traces of evidence there might be one, but they haven't seen it yet. These have very similar internal structures, not that far from being what Jupiter and Saturn, only on a smaller scale, but they are very, very similar. Okay. This, I think, is Neptune.
That is definitely Neptune.
That's definitely Neptune. Huh?
Says it in the
Yeah. And it's colored slightly differently, but it's Neptune. They don't show Uranus.
One of them has a ongoing storm. I don't know. But, I forgot which one.
This may be it right here.
Yeah, and the winds are super duper. Well, all the winds and all the giant planets are very high. But either Uranus or Neptune, one of those have the strongest wind speeds. I don't know.
Yeah. And I wouldn't be surprised because those things are moving out there. I mean, really great. The picture you see of in our book of Uranus, though, is this. And the weird thing about that, it's rotating.
Kind of like
Yeah, most of the rotation is on the same plane or close to it of the revolution around the sun. This is almost 90 degrees out. Not quite, but close to it. Notice it does have a ring. Like I said, all of them have rings, but they're very, very faint. But this one has a ring, but you notice the ring is so. And it seems to be turning backwards as well. Venus is definitely turning backwards. This one is at this, but seems to be turning backwards as well. So, interesting, bizarre, but true. Okay? We just don't know a whole lot about them. We do know more than we used to. Back when the book was written, we know more than it now because some of those probes, I don't think it's Cassini-Huygens, but some of the other probes have gone out and gotten a lot more data than we ever had before. And they also have, is someone going to say something? Oh, okay, I thought someone said something.
Dr. Fowler.
Yes.
Got 1 minute.
For taking the...
Here.
Yeah, okay. I'll take the roll again, but we're going to go on with the theory today and then have the test at the last part. Next time we'll have more time. Well, we've already had a little lab today because we finish the last one. So then we have theory, and then we'll have the test. And then next time we'll have some theory and then a lab. Okay. And it depends on if we finish today or not. We may have the test next time. Don't think we'll quite finish today, but we'll see. All right. But yeah, I need the stop and call roll at in just a couple of minutes. In fact, this may be a great place to stop. Let's just see these examples, if anything's worthwhile. All right. They're just playing around with numbers that we haven't done. So the next thing we're going to hit is the smaller bodies of the solar system. So this is a good place to take a break. Can we be back in less than 5 minutes?
We'll try.
Okay.
Is this where we're going to stop at?
What's that again?
Is this where we're going to stop at?
No, we're just taking a break. We're gonna keep going.
But this is where we're at?
Yes.
This is where what?
This is the part where we're at?
She's asking if this is where we're at.
Yeah, this is where we just finished Uranus and Neptune. Okay? Did you get all that?
Yes, sir.
Okay. So we'll start with this when we come back from break. Okay? And that'll be, try to keep it less than 5, folks, so we can move along. I'll actually turn this on. All right. So we've talked about, not that much about the sun, but in general we talked about the sun's formation earlier in the first chapter. And then we talked about the planets and a little bit about their moons. So now we're going to do the smaller bodies of the solar system that's not part of those basic ones. Not the sun, not the 8 planets, not even the dwarf planets, though we'll get maybe a little bit into that, but the smaller bodies and not even the moons around the planets. These are the smaller bodies of the solar system that are out there. Okay. Now, they comprise mostly 3 categories: comets, asteroids, and meteors. Now, I wish they wouldn't say meteorites. That's the wrong term to use here. They should say meteoroids, not meteorites.
What's the difference?
Okay. We're going to get to it later, but I'll go and give it to you now. A meteoroid is any object that's floating around out there, usually left over from a comet or an asteroid or something else, just a piece of rock, a space junk that's out there. It becomes a meteor when it enters the Earth's atmosphere, okay? And we see it ignite, and that's called a falling star, shooting star, something like that. That's a meteor. A meteorite is that if it was big enough, heavy enough, hard enough, that it didn't completely burn up in our atmosphere, if it actually hit the surface, that's what makes it a meteorite. So very few of these things are meteorites. The meteoroids are all over the solar system and may not ever come in touch with Earth. So therefore, meteoroid would be the better term here, not meteorite. Meteorite would just be a small fraction that actually land on the Earth's surface. Okay, so that's the difference. These are particles that were left over from the solar formation, the formation of the sun, and also the planetary formation, which we're going to talk about a little bit later. Okay? Now we're talking about the bodies themselves. Later we'll talk about how they were formed. But these are the leftovers. These are the scraps. These are the pieces that weren't grouped with the other pieces. Now this next bullet, I know what they're trying to say, but it's not quite accurate. Okay? The mass of the smaller bodies may be 2/3 of the total solar system mass. Now, does that not ring a bell with anybody right now? I pointed out at the very beginning of the chapter, page 379 in the paragraph, the last paragraph on page 379. When it says the solar system mass, what I think is the entire solar system, which of course includes the Sol, the sun. This cannot possibly be true if this first sentence in the last paragraph on 379 is true. The sun has 700 times the mass of all the planets, all the moons, and all the minor members of the solar system put together. So this is excluding the sun, obviously. Because the sun is 700 times all of it put together, so it can't possibly, this can't be 2/3 of the solar system mass. What it means is, except for the sun, the total solar system mass excluding the sun. The sun is by far the biggest mass. And then take that out of there, and then the smaller bodies added together could be as much as 2/3 of that. That means all the planets, Jupiter, Saturn, Uranus, all the planets, all the moons, all the stuff we talked about otherwise, this is twice as big as all those put together. Now, how can that possibly be true? There's so much of it. It's all tiny. It's all small. Okay? Now, what do these things do? Comets, asteroids, and meteoroids? They hit the bigger things. And here's the comet Schumacher-Levy, which was mentioned in your book back under Jupiter. The same picture, or one very similar, is shown here. Jupiter was such a strong gravitational field, it ripped the comet apart into at least 9 big pieces and some smaller pieces, and they then struck Jupiter July 1994. Now, how do we know this? Who saw it? Astronomers who were studying, the big national laboratories, the big national telescopes, observatories? No. It was discovered by backyard amateur astronomer who just liked looking in his telescope into the heavens. And he just happened to look one night at Jupiter. Jupiter was fairly bright, could see it, so he decided to look at Jupiter, and he saw these spots in a line like that and said, "What in the world is that?" And I think he may have taken, if not this picture, he took a picture of it and sent it to someone in the National Ocean and Atmospheric Association, someone, and said, "What is this I see on Jupiter? Is this an anomaly or something? Or am I imagining this? Or is there something wrong with my telescope? What's going on here?" And they said, "What is this?" And they all focused on Jupiter and found out that sure enough, and they traced back and they could do it, the comet Schumacher-Levy happened to be relatively close to Jupiter about that time. It got too close, pulled it apart, and it crashed into the surface of Jupiter, leaving this pattern. Now, I can't tell for sure where this is. I think that may be it right there, but I can't even say that for sure, where it crashed into the surface. So, that comet's no longer there. It's part of Jupiter now, but there are others out there. Many others out there. They're all tiny, and yet they have twice the mass of all the planets and moons put together. Okay? So let's first look at the comets. There are 2 big classifications of comets. There's a way out there comets. These are called in the Oort cloud. Okay? Now, they couldn't have made up that word. That must have been named after somebody. So there's a potential paper topic. Who in the world was Oort? Okay? What did he do? Did he have part of the involved in discovering these comets? What did he do? Be a good paper topic. Okay? The origin of the long period comets, those that come around once every greater than 200 years. So in other words, it's going to be generations between the time that comet shows up one time and it comes up around again. They usually count a generation to be about, 30 years? So this would be something on the order of 7 generations between visits by these comets. How far are they? 30 astronomical units, up to a light year away. Up to a light year away? A light year, remember, is how many trillions of miles out there? So this is 30 astronomical units. That's about the outer edge of Neptune's orbit to 1 light year away. That's huge. And if you can imagine that much of a cloud, a sphere around the sun, that big, it can have a lot of comets in it, and that can add up to a lot of mass. Okay? Now, a little bit closer in is, and I don't know exactly the pronunciation here, I would call this the Kuiper Belt. But I've heard someone call it the Kuiper Belt, which sounds rather bizarre to me. And I actually heard one professional call it the Jupiter Belt. And I thought to myself, after I heard her say that, I thought, have I misspelled this word? Have I misread it? No, she put an extra T in there and rearranged the order. It's either Kuiper or Kuiper. I don't know which it is. Who in the world was he? There's another potential paper topic. Well, these are shorter period comets. Those are less than 200 years between times they visit. And this is a disk-shaped region that varies from 30 to 100 astronomical units from the sun. So there is some overlap, but you see the Oort cloud is spherical, three-dimensional, whereas the Kuiper Belt is that disk shape. Remember, the planets are all on a disk. The Kuiper Belt just continues that disk beyond Neptune. Okay? Now, this is just a blown-up shot. You have sort of this picture in the book. It's a little bit different, but the very center of this is our entire planetary part of the solar system, with the sun being in the center, and then this would be the orbit of Uranus. That would be the orbit of Neptune. This is the orbit of Pluto. You see how out of whack that is? And there's sometimes it's inside the orbit of Neptune, and sometimes it's way, way outside. And then that would be just this little bit right in there. I mean, that's the entire 8 planets plus plus Pluto in there is in that little bit, and this is the rest of them. This would be the Kuiper Belt, and this would be the Oort cloud. Kuiper Belt goes from 30 astronomical units, which is Neptune, out to about 100 astronomical units, 3 times. Now, if there's another planet or two out there, it's probably somewhere in the Kuiper Belt. Okay? That would be my guess. Okay? And it's just so stinking far out there, I'm not sure. Sometime or another, if there's one there, they'll discover it. But whether it be in my lifetime, I don't know. And then the Oort cloud is all the rest of it, up to a light year away from the sun. That's out there. It's big. So, it's not even surprising that all these planets, Mercury, Venus, Earth, now the asteroids are counted in this part, then Jupiter, Uranus, Saturn, Uranus, and Neptune, okay, are also in here. Maybe even the dwarf planets are included. That's not very much. But all that together would be less than twice the mass of all that. Okay, there's a lot out there. It goes forever, and those things do orbit around the sun, And every now and then they'll come in toward the sun and then go way back out again. So it's a mess. The gravitational nudges deflect objects toward the sun. You know, one object getting close to another, it might pull it a little off track, and then once it starts heading to the sun takes over and pulls it in. It goes fairly close to the sun and then heads back out again for another 200 years, you know, before it ever is going to come back again. 200, 300, 400 years, some of them. I wonder if some of them have ever been nudged inward at all, but I guess they all have. Okay, so that's where the comets come from. Way, way out there. Oort cloud, Kuiper belt. What's the structure of these comets? Okay, now, by the way, folks, do not let me go past 5:15. At 5:15, I stop and you start taking your test, those who are going to take it today. So do not let that pass. Stop me a little before then so we can shut down today's lecture and go on and start on the test. So what are comets? They're small solid objects. There's a couple of models here. One is a dirty snowball model. Okay? And why they say that? There's frozen water involved. There's also frozen CO2, frozen carbon dioxide. What do we call frozen carbon dioxide? We have a name for it here on Earth. Yep. You're probably thinking the right thing. Yeah, dry ice, exactly. Dry ice. Okay? Frozen ammonia and frozen methane. We talked about liquid methane being on the surface of, which was that? Titan? Yeah, okay. This is frozen methane, okay? So very, very cold. Because these things are way, way out there. I mean, so far out there, they're not getting any radiation from the sun to speak of, okay? There could also be dusty and rocky bits in those frozen things, so therefore the dirty part of the snowball. This is the snowball part, this is the dirty part. Dusty or rocky bits in there. Okay? Now all the comets have a head where most of the solid gathers. There's the nucleus, but then around that is a coma of gas. Okay? Some of this as volatilizing. The actual word for it is sublimating from the solid state to a gaseous state. So that's a coma of gas. And you get two types of tails. The comet head and then one or two types of tails. You have ionized gases. And remember what an ion is? Okay, say it again.
Two bonds.
Okay. Yeah, it's an unbalanced atom. It's either gained electrons or lost electrons. Ionized. That's what makes it ion. They're charged, either positively charged or negatively charged. Either lost electrons or gained electrons. Lost electrons became positively charged, gained electrons, negatively charged. So these could be ionized gases, like the gases flying through these fluorescent tubes here, or in stars and stuff. Those are ionized gases. Okay, or they're just dust. And the dust is reflecting light from the sun. It's not creating its own. The ionized gases could be creating their own light like this is. Okay? But, now here's a picture of a comet. Okay? Which way is the sun? Lower left. The sun is down here. The head of the comet is always pointed toward the sun. Which way is this comet going? Toward the sun or away from the sun? We can't tell. Because even if it's going away like that. The head is always pointed toward the sun, and the tail is always away from the sun. Whether it's coming in that way or going out that way, it looks the same. Don't think, I mean, there's nothing that's going to make it look like this except the light from the sun. So it could be going in, coming in, or going out. It's going to look just like that. The sun is down here. It always points toward the sun. The head does. The points away from the sun. Okay, this is the dirty snowball here, and this is the gases. It could be ionized gases creating its own light, or it could be dust particles that is reflecting light from the sun down here. Okay. Only when it gets close to the sun does it look that bright. Okay. Now, what's the most famous comet in your mind? Schumacher-Levy got famous when it crashed into the sun, but we never thought much about it. I hadn't thought much about it before. But one of the most famous is Halley's. So a lot of people call it Halley's Comet, but it's Halley's Comet. It came through, and it comes through about every 70 years. It came through last about 85 or so, 1985. The time before that was early in the 1900s, and this is what made it famous. This in the previous time. It was bright. It was spectacular. The time before that would have been the 1830s or so, and the time before that would be the 1760s or so. And somewhere back there, it had come through, and about every 70, 72 years, something like that. One time it came through, and it was so bright, people thought, end of the world is coming, whatever is happening out there, that's the great light shining and all this kind of stuff. Of course, it was just a comet. Okay? And then subsequent times, it's been either closer or not closer, but most of the time further from the Earth. When it came through, and it came through with much press, much anticipation about seeing Halley's Comet. The last time it came through, it was kind of a dud because it was so far away. You had to have binoculars. You might be able to pick it out, but you really couldn't tell if it's a small aircraft or if a comet. You know, you had to have a pretty good set of binoculars and say, "Oh, yeah, that's a comet." Nowhere enough to people think it's going to be the end of the world type thing. But it happened about, I think it was around 85 or so was the last time it came. So it won't come again until around 2050 something. I'm not going to be here. Okay. Y'all might, but I'm not. Okay. Were y'all around in 85?
I wasn't. No. I wasn't even born.
Yeah, that was it. Y'all might see it the next time. I was alive when it came through last time, and I'm not sure I ever saw it. There was one time I looked up, and I thought I saw something white moving out there, but I couldn't be sure. I thought it could be a plane, you know. But people with good telescopes and binoculars, they saw it. It was it. So which kind was that? Where did it originate? Kuiper Belt. It had to be Kuiper Belt. Anything less than 200 years would be Kuiper Belt. Okay, Schumacher-Levy was probably Kuiper Belt. There aren't many that we know of the other. Okay, so there is a comet. And more than likely, that was probably what Halley's looked like time before last or a few times before that. It was spectacular. Not last time, though. Okay. Man, that's all they say about comets. Okay. They have a little bit different picture in the book, and they do mention Halley's in the book. Observations from the Vega and Giotto spacecrafts found the nucleus of Halley's Comet to be blah, blah, blah. So you got some more information there than what you had in the slideshow. So let's move from the comets to the asteroids. Okay, whoops, too much. The asteroids really feel like part of the inner part of the solar system because that's where they are. The comets are way, 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 way out there most of the time, and every now and then make a trip through. Okay? Now, the asteroids are that belt located between Mars and Jupiter. Just a bunch of rocks floating around out there. Now, believe me, they're not very close together, okay? You probably, if you were on one, you wouldn't see the next one. They're too small, but we picture them as being a pretty big mass of them. But remember, the distances are so far. They can be, the size is up to 1,000 kilometers, and a couple of those, I'm trying to think, I think it's Ceres, is actually a dwarf planet. It's probably right at or bigger than 1,000 kilometers in diameter. Now, very composition. The inner belt, what is the inner belt of the asteroid belt close to? What planets do we call those? Those are the terrestrial planets. Those are mostly rocky planets. So it's not at all surprising the inner belt of the asteroids are stony chunks of rock. Okay? The outer belt is dark with carbon. Now that to me is not parallel. I don't know. Others in between are iron and nickel. But iron and nickel is what most of the planets are made of. Remember? The core part, the solid part, are iron and nickel. Dark with carbon on the outer side. I can't think of why that would be the case, except they might be a little bit lighter so they get thrown further out the door. The stony ones get pulled in. Okay? Now, again, and we're going to go over this later, we think they were formed by the original solar nebula, which probably blew out as the sun was exploding and then contracting and stuff, blew out the materials. Part of it clumped together to be planets. Smaller clumps became moons of the planet, but for some reason this belt here, and here's what the reason is, we think it was prevented from clumping because Jupiter was too close, too big, too much of a gravitational field to let them clump like the rest of them did. Later we'll see pictures of the clumping. The asteroid belt just never clumped like the rest of them did. Okay? Now, here's a picture of this. Sun here. Obviously the scale is not right. The Mars, remember, we say was 1.5 astronomical units out there. The Jupiter is out here at 5 astronomical units. Just about midway between the Sun and Jupiter is the asteroid belt. So that would be right around 2.5. But the inner part of that, maybe around 2.4, somewhere in there, would be the inner part where the stony asteroids would be. The outer part, the darkly carbon part, would be about 6 tenths. They would be about 2.6 or so astronomical units out there. Okay? So 1.5, 2 something another, 5. So you see the relative scales right the same. Mars didn't bother them at all. Jupiter bothered it big time. Okay. Now remember, Mars has 2 small moons. My guess, there are a couple of asteroids that got too close to Mars, and Mars picked them up and they became moons. Jupiter could have up to 50 moons or so. Jupiter probably yanked off some asteroids, and that's what made some of it. Okay? Hard to say. Guesswork. But I think reasonable. All right. So there's the asteroids. Now they're counted with the smaller bodies. They're not nearly as big as the planets and generally not as big as the moons. But they're part of the smaller bodies, which includes comets, which are way out there, sometimes coming in. Asteroids are just always in the same place. But every now and then, one of these, I don't know what happened. They maybe bump into each other or something, loses some momentum, and once it starts falling, it's going toward the sun. Now, I don't think it was more than 5 to 10 years ago, and they think it was an asteroid, not just a meteor. An asteroid crashed into somewhere out in Siberia in Russia. I don't think anyone was hit, but it was fairly close to a town, and they just thought, what is going on? Has someone started a war or something? Because it was an enormous landing and probably felt for quite a distance, and sound was enormous, and they went out and checked, and sure enough, it seemed to have been an asteroid. If that had been near a population center, Moscow, Tokyo, Seoul, any of those places, man, that would have been worse than Hiroshima or Nagasaki. I mean, we dodged the bullet in some senses. Okay. So those are the asteroids. Now we get to the meteors and meteorites, but actually before that, the meteoroids. Okay? Now, basically, that's just pieces of rock that are floating around out there, not part of the Oort cloud, not part of the Kuiper belt, not part of the asteroid belt. These are just junk, remnants. One time may have been a part of a comet, maybe was part of an asteroid, but just is floating around out there. And there's plenty of it. I mean, there's a lot of it, but it's way far apart, and they're really small. You hardly ever see them. Those are the meteoroids. That's what I thought that first slide should have said, not meteorite down here. So, when does it become a meteor? When it encounters the Earth's atmosphere. A meteor is the thing when the meteoroid encounters the Earth's atmosphere, the gravitational attraction of the Earth pulls it in, has to go through the atmosphere, usually at pretty high speeds, it burns it. I mean, it ignites it. Okay? It glows. It falls apart. Okay? It vaporizes. Whatever terms you want to use, that's what a meteor is. You actually see it, shooting star, falling star, that's what we call it. And there are certain times of year when we have more meteor showers than normal. And that's usually because we're passing through. Now, we didn't say this. The book didn't do a great job of this. The book did an okay job, but the slide set didn't do a great job. When those comets are coming in, okay, remember they have that, the nucleus, the head, and then the tail. Some of the tail is being left behind because you see, remember it was a dirty snowball, and as it comes closer to the sun, some of that snow melts, okay, and the dirty part gets released, and that goes into the tail, and that gets left behind, okay. Well, when one of those has passed and left all that junk behind, when we happen to be in our orbit around the sun and pass through one of those places a comet came 50, 100, 700 years ago where it left that junk there, we're going to have a lot of meteors then because we're just passing through an area where those meteoroids are just hanging around. They're just out there. We pass through, and those that enter the Earth's atmosphere, we see the meteor showers. Okay? It's not the actual comet tail that was part of the comet, it's what's left when the comet passed. The meteorite, though, is that portion, that meteoroid, that came into the Earth's atmosphere, became a meteor, and made it all the way to the Earth's surface. And these meteorites are either iron, stony, and the stony ones can either be chondrites or achondrites, or they're stony iron. Okay, so some combination of those. And if you think about it, this is exactly the type of thing we think the asteroids were. They're either stony, if they're close, they're whatever dark with carbon out there, or they're iron to iron stony in between. Okay? So this is what they usually are. Now, what are the chondrites versus achondrites? Okay? I'm going to read it to you from the book, so I'll get it right and you'll get it right. Chondrites have a structure of small spherical lumps of silicate minerals or glass called chondrules, and therefore they're called chondrites, held together by fine-grained cement. The achondrites do not have chondrules, so therefore they do have a homogeneous texture, more like volcanic rock, such as basalt or cooled from molten rock. Now that's not very descriptive to me. But if any of you, I know that a lot of Birmingham and Bessemer area has had a whole bunch of mining and blast furnace and things like this. Have any of you ever seen the slag that was left over after things, especially when coal is being burned? Coal is not very pure. It's mostly carbon, but not totally carbon. It has some silicates in it. And when you burn coal, it gets very hot, and the silicate actually melts and then forms back again and forms these little spheres. They look like ball bearings. Have you ever seen that material? It's usually called slag. Okay, I don't know. And I'm not sure about this. This is my guess. When you're coming around Arkadelphia Road on 2059, there's a huge mound somewhere off there on the north side of 2059. And my guess, that is slag left over from years and years of blast furnace and things like this. I bet you if you got that material and looked at it, you'd find they're almost all little round beads. Okay? That's what a chondrule is like. It's a silicate material that must have gotten very hot at one time, melted, and then reformed. And when it reformed, it formed little spheres, little beads. The achondrites never did. They're just little chunks that are not necessarily spherical. Same type of material, but not that. So the stony ones can be either chondrites if they have the little spheres, achondrites if they don't. And then a mixture of stony and iron. Not a very clear description, but that's what they've got. Okay? So the meteorite is the meteor that actually made its way to the surface. The meteor is a meteoroid that entered the Earth's atmosphere. Okay? Now, here are the times when we have the biggest meteor showers. One of the bigger ones was back on January 3rd or thereabout, when it was maximum, is quantratid. The tid means it's a meteor shower. I don't know why that's the suffix for that. There must have been some constellation there called Quandra or something like that. So back then, about one every 2 minutes, you would see a shooting star. If it's a clear night, not many clouds, around January 3rd, cold then, don't know what time of night, hopefully not too late, okay? Aquariid must be in the constellation Aquarius, May 4th, but that's about one every 12 minutes. I think I get kind of bored waiting 12 minutes and maybe see a meteor, okay? Perseid, there is a constellation out there called Perseus. It's going through that one on August 12th. 40, that's about one every minute and a half, okay? About one every minute and a half. I could probably stand that. August 12th, nice temperatures, in between terms maybe, so that would be worth staying up and watching that. Actually, it didn't happen too long ago, and I remember we were over in Georgia, and I remember hearing about there was a meteor shower, but I worked so hard that day. I think we were cleaning our porch, getting ready to paint it. I was out. I didn't stay up and watch it. Should have, but I didn't. And I think it was cloudy that night. Orion, one of my favorite constellations, so easy to pick out. That one on October 22nd. The next one coming up, but it's going to be one about every 4 minutes. Okay, it's going to be kind of boring. Having to kill 4 minutes between hopefully seeing the shooting star. And it has to be a clear night, that kind of stuff. Taurus the bull. Second.
I said, that's my zodiac, y'all. Taurus.
Okay. November 1st and again on the 16th. We must pass part of it one time where it came in and part of it where it went out in the next one. I don't know, but only one every 12 minutes. Lord. Okay. Leo the lion, meteor shower in that around November 17th, the next night, but again, only once every 12 minutes or so. But the biggest one in Gemini, which I'm not sure I can pick out Gemini, it means the twins, December 12th, the end of this term. I think we'll already be through finals. This class will be longer over many terms. Almost one a minute. What's that?
That's why we best.
Oh, of course, yes. Okay, all Gemini being the best. Okay, so that's when you'll be most likely, if it's a clear night on December 12th, and not too awfully cold that you can stay out there, you might see quite a few meteors that night. Okay? Now, here's some pictures of some of those, and these are not quite the same pictures as the one in the book, but the first one there, I think is supposed to be a stony meteorite. Okay? Now that looks awfully dark to me, but it's stony. Now, things to point out about it, this part over here looks like it could be the chondrite type. It looks like those are made up of little beads. Okay? The face over here, though, is slicker. That's more like a glass. Okay? Like volcanic glass. Okay? So this side could be the chondrite, and this may be a chondrite. I can't tell for sure. Now, near where we live in Georgia, where I grew up in Georgia, that's where our farm still is, and we have a little place over there, a 2-bedroom bungalow, we still have our interest in the farm. You find a lot of dark-looking rock, some of it almost glassy-looking like this, and it's just scattered through the woods and the streams and stuff there. And there is a theory that a pretty good-sized meteor ride actually may have landed there. And they say if you look at a topographic map, you can almost imagine kind of the crater that happened there. I don't know. But we have found quite a bit of that. Other people think it's just what they call bog iron, and that may have formed the same one. Now the second one there is and by the way, the smooth black surface was melted by compression of the atmosphere. The second one there, they say, is an iron meteorite that has been cut, polished, and etched with acid. So it doesn't look like iron to me, because iron you expect to be dark, but they cut this, polished it, and then etched it with acid, and that's what the white is. That's not what iron that would look like if you found it on the rock. You know, if you found it just out there. So I wish they had shown one that hadn't been all that done to. Okay. But anyway, there's your meteors and meteorites. Now, what is it? 4:35, right? Okay. So we got some time. Let's look at how we think the solar system came about. We've talked about how a star was formed, the masses of gases, the nebula, and then they got lumped together from some sort of perturbation, something that made gravitational collapse. If that continued to the point that it got hot enough for fusion to start, then it became a protostar. That's going to become a star. That masses of gases will not necessarily be a star. The nebula may not ever be a star, but when it gets to the protostar, that's when it starts. Well, that's the beginning of explosions and bringing together and collapsing and coming up. This is when I think the protoplanet nebula model begins. So let's look at stage A. Okay? Your star is just probably a protostar now. It's exploding, it's sending stuff out, it's coming together, it's doing things. The formation of the heavy elements in many of the earlier stars and supernovas come together. They have some radioactivity that produce heat. The coming together, the friction is heat. The pressure creates heat. The nuclear fusion is started. So you get the things coming together. The concentration of one region in space of dust, gas, and chemical compounds, and it's centered around sort of a nucleus, and then it has this band going around it. And I don't know what it is about it. I think it's the fact that it's spinning, that you have that plate-like band around it. But that you do. Okay? So that's stage A. Just the beginning of it. Okay? You can't really see what's going to be a planet or not. You just know it's something in those bands. Stage B then, oh, did y'all need it? Sorry. Okay. So, now maybe the star is already formed. Maybe it's through the protostar phase. Maybe it's actually reached its final, but it's still incredibly hot. It's thrown stuff out there, it's floating around out there, and it's all pretty much gaseous. There could be some solid in there, but not much, but mostly very hot from recent nuclear explosions. It's not coagulated yet, you might say. Okay? That's the stage A. Very early in the formation. Everybody got it? No, still writing? Okay. Take your time. Okay? Still writing? Everybody got it? All right. Stage B. The formation of a large rotating nebula. Okay? The sun, the star in the middle, is basically coalesced. It's pretty much become what it's going to be, but the stuff that's going around is still masses of gases. It's not really accumulated yet. Okay? The gravitational contraction is still happening. The spin rate is increasing. Most of the mass is concentrated in the central. Okay, so it's still protostar. Now, I would have said that's the protostar. This looks more like a star, but they say it's still in the protostar. Most of the mass is concentrating there, like 700 times more than all the rest of it put together. It's still there. Okay? But the remaining period forms pretty much in this accretion disk. Now that to me looks like this too, but they're saying this is the B form. It's not solid yet. It's too hot. It's too recent. Okay? But it's beginning to sort of group together. Now, they're just showing the four inner sort of terrestrial planets. This isn't necessarily our sun. But if you can imagine, that could be the four interior planets. Okay? You have this big one out here, big massive thing, that keeps that next band from clumping, going together. That would be Jupiter and the asteroid belt. And then the others are on further out. Okay? The remaining material forms in the accretion disk. The material in the accretion disk begins clumping together. At least the inner four did for us. The next one just would not clump, probably because of Jupiter. Okay? They're only showing the inner four. Okay? Now, the others are sort of forming. Now, it's kind of easy to imagine that some of this could be form a planet, and some of the rest of it form a moon. That didn't happen in the inner two at all. It may have happened to Earth. It may have happened to Mars. 2 little bits fell off. I still think Mars probably just stole a couple of asteroids. Okay? But who knows? There's another theory about our moon and Earth. We'll talk about that in the next chapter. Okay? So that's the B, stage B, basically still in the protostar stage, and the masses that were in the disk around it are sort of just clumping together. They're still gaseous, they're still hot, they're still not formed, and supposedly that next band out there never clumped, came together. Okay? Now, notice this isn't clear and precise like this. There's probably still explosions going on and stuff flying around and stuff being pulled in and stuff being shot out. It's a busy time. It's an unstable time. Okay? Stability doesn't start happening until group C, stage C, where we haven't quite gotten there yet. Now, if all this was happening because of nuclear explosions and things like this, very massive things, it's going to take a long time to cool. And there's nowhere for it to go, so it cools very, very slowly. Okay. All right, everybody got it? Someone still writing? Okay. So let's go to stage C. All right. Finally, that protostar settles down and becomes a sun, a star. Okay? Main sequence star. Beginning its life as a star. Now, guess what? You can still have these solar ignition flare-ups. Okay? They may have happened in the earlier stage, and one of those, just like you were saying, may have hit Mars and blown away most of its atmosphere. Hey, it probably hit Mercury and blew all of its atmosphere off. Okay? It's so close to the sun. Really, really likely to have happened. So the solar ignition flare-up may have blown away the hydrogen and the helium atmosphere from the inner planets, leaving just the denser gases like no atmosphere or carbon dioxide, which you find on a lot on Venus and some on Mars, Mercury. Everything got blown away. The lighter gases got blown way out there, and that was picked up by the gas giants, Jupiter, Saturn, Uranus, and Neptune. And maybe the next one or two out there. Okay? Now, the protoplanets, they're still too hot to be called a planet, but they're separating the heavy and light minerals. The heavier minerals going toward the center, and the lighter minerals staying near the surface. We'll talk about that in 2 chapters. Okay? The larger bodies cooled more slowly, with the heavy material settling over longer times into the central cores. That's probably what happened with Jupiter, Saturn, Uranus, and Neptune. They are larger, so they cooled more slowly, but they're further from the sun, so in that sense, the cooling may have happened a little bit. But the heavier stuff went into the cores, the iron nickel-based core, and then the gases in the outer part. Okay? Same with us. Our inner core is iron and nickel. Outer part has more aluminosilicates and actually water on the surface. So yeah, the lighter stuff is further out. We'll talk about that in a couple of chapters. Okay? So now we're beginning to be the solar system as those larger bodies are cooling. Part of that is radioactivity from the explosions that push them out there. Part of it is heat from just grouping, clumping together. Now, the question is, did any of these 4 inner planets have moons? Mercury, I don't think ever did. If it did, it got blown away when the atmosphere did. Say again?
Earth did it until it got hit.
Earth did what?
Did not have a moon until some planet had crashed into it.
Okay, and that is a theory. I was going to suggest it. We're going to talk about it in the next chapter. There is a certain amount of really good evidence that indicates Earth didn't have a moon, and it probably was an asteroid, I'm guessing, that crashed into it, or some enormous piece of space junk and actually broke the moon off. Now, that could have been at this stage, or it could have been at this stage. Who knows? We don't know. And Mars, like I say, I'm really suspicious they didn't just pick up a couple of asteroids that had fallen out of orbit. Who knows? Okay. Everybody got it?
Got it.
Okay. So, here are some of the ideas about the solar system. Some of these are a bit close to being wacko. Early on, as would be a normal way of thinking, we thought, of course, we were teenagers at the time. We thought we were the center of the universe. No, that's not what I meant to say. Okay? We thought everything revolved around us. Okay? Evolved or whatever. And it looked that way, didn't it? I mean, you sit here on the surface of the earth, you watch the sun rise in the morning across the sky and set in the evening. It looks like it's going around us. We look at the stars, and except for the North Star, it sort of stays fixed. All the others seem to be turning, so they seem to be going around us mostly. Okay? Everything, the moon goes around us, everything goes around us, so why not think we're the center of everything? And everything else is going around us. It makes sense. Except for those pesky little planets. Okay? The attempt by some of the early Greek astronomers and philosophers to explain the observed motions of the sun, moon, and stars. The sun definitely looks like it goes around us. Slightly strange pattern, but goes around. The moon definitely goes around us, and it really does. The stars look like they go around us, except the North Star sort of stays in place, and those other do strange things up there. But those crazy little planets. Some of these early models placed the Earth at the center of the orbits of the planets. But the planets didn't behave well. In fact, that's why they were named planets. The word planet comes from the Greek word meaning wanderer. Because sometimes they look like they're going around the Earth fine, but then all of a sudden they slow down and stop, and then turn and go backwards, and then turn and stop and go back again, and then go around the Earth fine. So they sort of get lost. They do funky things. And no one could really figure out why. Okay? So what a guy did, a guy named Ptolemy, and he was an ancient Egyptian, I believe it was, astronomer. He took that basic geocentric model and started trying to play with some ways to explain those weird ways the planets were moving. And they worked for a while on the short run, but after a while they fell apart. Inconsistencies in the system grew in number, became complicated to explain. They tried, Lord knows they tried, but they never could quite get it right. And here's part of the problem. I've never found the verse either, okay? But I guess somewhere in the scriptures, something was said about going around the earth. And somebody then said, everything goes around the earth. It says so in the Bible. And frankly, I've never found that. I've read the Bible several times. I've never found where they got that idea, but they believed it from the depths of their being that this was it, that we were the center of the universe. Everything went around us. And therefore, it became a very difficult thing to challenge. Now, somebody's still writing. Okay. Huh? Does that mean anything?
I'm trying to roll my hand.
Oh, I see. Okay, printing. Okay. I thought you were giving me a signal. I thought I was supposed to steal third or something. I don't know.
I was no. I've been writing non-stop, and it's giving me a dang hand cramp.
Okay. Okay. Now, it's sort of sad that some really big hindrances to advance of science can be blamed on the church. And I'm not sure the church can take all the credit for it, but unfortunately, there's too much that it can be responsible for. For instance, I think I mentioned before the great library at Alexandria, Egypt. Just an incredible collection of Arabic and even Hindu and European and Middle Eastern and just all over, gathering together all the beliefs and the structures and the science as best they could do it at their time, brought together under one roof. It was just a fantastic thing, and it was overrun by a zealous group of probably pretty uneducated Christian soldiers that decided, well, this is pagan, it has to be burned. And they burned volumes and volumes of ancient wisdom and knowledge and stuff. No! Why? It was ignorance, unfortunately. Here's another. Now, the irony that I find in this is going to come up in the next slide. Because guess what? In Europe, the church was the one thing that kept knowledge alive in Europe. In the Dark Ages, ignorance was rampant. It was only the church that the people could read, write, the priest, and they interpreted and read and dealt with all of the structure. Well, here came the heliocentric model. The idea that the earth revolves around the sun came from this guy named Copernicus. Does anyone know what his job was? He wasn't a professional astronomer. He probably did a lot of looking at the heavens. Do you know what his real job was?
What did he got? Newspapers?
Say again?
Newspapers?
No, actually, this is way probably before newspapers were in existence.
Should you like sit around and like talk or something?
Okay, what?
They just used to like sit around and talk about this stuff or something.
Okay, a philosopher type person? Probably was, but actually what he was a monk in the church. But he was way out there in Poland, where the center of the church was in Rome. And he was up here in Poland, he was a monk, and he was a brilliant guy. He studied things, and he said, look, it looks like to me that all these inconsistencies in Ptolemy's model, all the things that are impossible to iron out, it would all come out into play if you had the earth going around the sun and the other planets going around the sun, and then the stars are just way, way out there. And sure enough, that's the heliocentric model for our solar system. Helio meaning, geocentric. Okay, let's go back to the slide just for a moment. I'll come back. The geocentric, geo meaning earth, earth being the center, heliocentric, that's sun, helios, sun is the center. And it was developed by a monk. Now, he wasn't about to publish it because this went against the teaching of the church, and he worked for the church. But he wrote it up, and he had an assistant, and I can't remember that guy's name. And as soon as Copernicus died, that assistant wrote this stuff up, giving Copernicus the credit for it, because he's the one who did it, and published this. And, of course, they couldn't punish Copernicus. He was dead, okay? But, and they couldn't really punish the other guy, because it wasn't his work, it was Copernicus's. So they got away with it, Okay? And this other guy, Galileo, read it. Galileo said, hey, this is making a little sense. And once Galileo perfected that telescope that someone up in Europe, Northern Europe, had invented, perfected it, and looked out there at Jupiter, guess what he saw? Jupiter was rotating. And he looked at the other planets, and they were rotating. And he said, wait a minute. If they're rotating, why aren't we rotating? And if we're rotating, that means the sun looks like it moves like this, where the sun is here, and we're just turning. He said, wait a minute, does this ever make sense? But unfortunately for Galileo, where did he live? Italy! Pisa, Italy. Way too close to Rome. And when he came out and supported this, they were ready to execute him. But he was such a famous scientist, had so much credentialing, they just put him under house arrest. And they forced him to recant his writings. So he gave it lip service and said he recanted, but sat in house arrest and wrote, I really don't recant this. This is indeed true. He kept studying it and stuff and just didn't publish his until after his death. It was happened already.
Like, I think they nailed him to the cross and set him on fire, didn't they?
Possibly. They were really close to executing him, but they didn't. Thank goodness. So anyway, the inconsistencies of the geocentric model were explained by this heliocentric model, and here's why. Okay? Let's look at Earth. We're revolving around the sun here. And at the same time, Mars is going around. Mars was really a big problem for us. Mars is going around the sun too. So at this point, Earth is here and Mars there. So up in the sky, it looks like Mars is here. Then a little bit later, Earth is here and Mars is there, and it looks there. Yeah, it's following a very definite pattern. Good job, Mars. Way to go. And then Earth is here and Mars is there. Yeah, it's still following that track pretty well. And then later, Earth is here and Mars is there. It's getting a little ahead of itself, but it's still following a good pattern. Until here. Now we skip a little time here. Earth is here, Mars is here. Uh-oh, it's going backwards. Why is it going backwards? Nothing goes backwards. And it did. And then at 6, a little bit later, Earth is here, Mars here. It's going further backward. And then Earth 7, Mars 7. Oops! It's turned around and started going ahead again. And now it's going pretty regular again. So it was regular, backward, regular. But that couldn't be explained by Ptolemy's geocentric model any way, shape, or form. But if you do this, it makes perfect sense. Mars isn't going around the Earth. There's certain parts of the year where it seems like it might be, but it's actually going around the sun. It's just going much slower, much further out than we are, so it seems to have different positions. And all the planets could be explained this way. Okay. Now, along came someone else. Johannes, I think his name was Kepler. I believe he was German. Okay? And Kepler actually he was quite a mathematician, a geometer, a trigonometer. He put together a system of laws that would further explain the heliocentric model. Even Copernicus didn't quite have it right. Notice this, they all look like circles around the sun. And there were still problems with it. Not nearly as major problems as what the geocentric model had, but this wasn't right. Well, Kepler was able to fix that. He said they're not really circles, they're ellipses. Not very much off from being a circle, but the sun is at one of the two foci. An ellipse has two foci. A circle only has one, focus in the middle. An ellipse has two. Now they're really close together sometime, and the sun was at one. That explained the little discrepancies you had before. He also noticed that when they were coming in close to the sun, they sped up. When they were further out, they slowed down. And that made perfect sense too. Okay? Sort of. He just saw that it did. And he came up with these laws that, fit it to a T. The problem is he had no clue of why these were true. He came up with the rules based on his geometry and his trigonometry and stuff. He saw how they worked, but he couldn't tell why. And he went up to England, somehow, maybe he wrote a letter, I don't know, asking this guy up in England, let's see, what was his name? Isaac Newton. Can you figure out why this might be true? Well, Newton started looking at them and started doing some figuring. The problem is the math of his day was not strong enough to support the ideas that he had. So he had to come up with a brand new branch of mathematics called calculus. That's where we get calculus. He came up with it so he could describe Kepler's laws, give a reason for it, and sure enough, everything came together. Further explaining the heliocentric model. Oh my goodness, the last slide.
Yeah, we got about 14 minutes.
And we got about 14 minutes. What's that? I can't quite. But yeah, the test is mostly multiple choice, right? Okay. Now, I think the first test is all multiple choice. I can't remember it in a while. But I did want to point out some things that are not in the slide set. And these, parts of them are Kepler's laws, and then parts of them are some other guys that did some things. And here's the first one. The first part of Kepler's law said the planets are not circular orbits, they're actually elliptical orbits. Now, there's not a single planet I know that's that elliptical. This is a blown-up thing of it. Two foci, one of them being the sun. And the planet out here is sometimes further from the sun, sometimes closer to the sun, sometimes further from the sun, sometimes closer. Next chapter, we'll talk about this in more detail. Okay? Now, the second part of that, and he observed it, but he couldn't tell why, that when you're closer to the sun, in a given time period, you're going to cover an area, this is called the sector of that ellipse, that's of equal size at the same time here. But you're going faster here, slower here, but the area is the same. And again, this is greatly exaggerated. None of them are this big. Well, that is Kepler's second law. And then the third one had to deal with the distances and the the speeds at which they're going around, that kind of stuff. So he came up with these three laws, but he had no idea why they were true. And that's what Newton contributed. Now, the book doesn't go into that. But here came somebody else, a guy named Tycho Brahe, okay? And he decided, I think this is it. No, actually, this was Kepler again. Kepler has his third law is that the period squared is proportional to the distance cubed. Weird, but true. But he had no idea why this was true, but he saw it was true. And he did a log-log plot, which takes the powers and makes them into linear. And look at here. If you did this for all 8 planets, here you have Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. Look at how nicely they're spaced. Again, earlier I said Earth and Venus seem too close, but here is Earth and Mars seem a little too close. And sure enough, it looks like there should be a planet right in there, right where the asteroid belt is, that Jupiter kept from forming, and that would have fit right in there and made a perfect straight line on the log-log scale. Okay? It's easy to imagine there could be another 1 or 2 planets on out here. It's just No one thought of that at the time, but it sure seems like that could be it. Actually, as it turned out, I don't think Uranus or Neptune had been discovered at the time that he did this. And when they were discovered, they fit the model perfectly. Never would something like that have happened in Copernicus' model because it just was faulty from the get-go. But in this model, it is perfect. All right. Another person behind the science, Gerard Peter Kuiper. And again, I don't know how to pronounce his name. I'm saying Kuiper. He was born in the Netherlands, Dutch born, but he came to the U.S. and became an astronomer here. Great blurb here on him. This cannot be your source for your paper. The idea can be your idea for the paper, but you have to get your source outside the book. Now, if you read much of this, you'll see there's some other things mentioned here. Not as many as some of the others are. So, yeah. You might see some other potential paper topics from the Greek. Okay, now what this means, we just finished the chapter, haven't we? All right, that means on Thursday, okay, we have the test on chapter 14 today. On Thursday, we're just barely going to get started in chapter 16. We'll only have class for about 2 hours on chapter 16. Then we'll have the lab on chapter 15. I doubt if it'll take you 2 hours. We're going to do it as a group just like we did before, but it's not nearly as long as the first lab was. Okay, so we'll probably finish that in less than 2 hours. And then we'll have the test on chapter 15. Okay, sorry about it 2 days in a row. But those who don't take the test today, if you want to take them both or just this test, Thursday we'll work that out, however we will. So today was long on lecture, short on test. We had a little bit of lab time at first, then lecture, then test time. Next time we'll have a little bit of lecture, a little bit of lab, full lab, and then a little bit of test time.
Excuse me, what time is it?
What's that?
I was asking what time is it?
Oh, what time is it now? We've got about 5 minutes before it's time to start the test.
Our lab for this will be next time.
Will be next time, okay? We'll start chapter 16. Now, let me say this about the chapter. I'll say it to everyone, but I want everyone to hear it since a couple of you are new. Nothing replaces what? Reading the chapter. In fact, I do it a time or two just to make sure I got everything straight. Maybe 3, okay? There is a summary here which summarizes some of the big points. Certain words are in italics. Those are pretty important to pay attention to. You also have key terms here. It's a fairly good list, about normal or a little more than normal. Then we have applying the concepts. These are all multiple choice questions, 41 of them, which is maybe not quite as many as some chapters have, but they're good questions. Study those. You'll have a good shot on the test. You'll not see probably any of the test questions here exactly, but you'll see some related to it. So if you understand why these are true, you'll probably understand the ones on the test as well. Then there's questions for thought. There's 19 of these, which is probably a few more than normal. For further analysis, 6, maybe a little bit longer than normal. And then there's the parallel exercises, which really aren't, to me, all that useful. But if you really get into it, you may find those worth looking into. So we only have about, 4 or 5 minutes left? That's not really time to start.
5:08.
Yeah. 5:08?
Yeah.
So we got 7 minutes left. You want to get started in 16? You want to get started on your test? Okay. We'll give a little break today. We'll start next time on chapter 16. So let me